There is a monster in the depths of the cosmos. Not a beast of flesh and bone, but one forged from gravity itself, an invisible titan whose pull distorts the fabric of space and time. This creature spins faster than nearly anything else in the known universe. So fast, in fact, that its edges almost touch the speed of light. At its heart lies a darkness no light can escape from. And around it, an arena of extreme forces, furious energy, and shattered physics. This is not science fiction. This is a real black hole, MCG 6-30-15, a cosmic object that challenges the very limits of Einstein's equations. It does not just sit in space like a passive void. It spins, and it spins so violently that space itself is twisted in its wake. Imagine something with the mass of millions of suns, compressed into a single point, spinning at nearly the speed of light. Imagine the boundaries of time and space breaking down near its edge. That's what MCG 6-30-15 is. But before we continue, subscribe to the channel so you don't miss out on any of these videos. In the visible universe, most black holes are invisible beasts, detectable only by their influence on their surroundings. But MCG 6-30-15 gives us something rare, a signal. A flickering beacon in X-ray light that whispers of the unimaginable forces at play. This signal reveals warped light, bent time, twisted space, and one of the most extreme gravitational environments ever observed. It is, in every sense, a cosmic tornado, spinning with such intensity that it blurs the boundary between reality and theoretical limits. MCG 6-30-15 is not merely interesting because it exists, it is because it pushes what we thought was possible. Its X-ray emissions are not just strong, they are distorted, stretched, and curved in ways that scream of relativistic effects. And those distortions tell a story of a spinning black hole that defies calmness, one that drags spacetime in its rotation, that twists the orbits of anything nearby, and might even hint at new physics waiting to be uncovered. It is a monster that not only devours matter but also gives us a window into the deepest workings of gravity itself. This video is a journey into the abyss, not to fear it, but to understand it. A dive into one of the most extreme places in the universe. A place where time slows, light stretches, and reality itself spirals. Just over 130 million light-years from Earth, in the southern constellation of Centaurus, lies an unassuming galaxy named MCG 6-30-15. To the human eye, this galaxy is invisible without a telescope. There are no grand spiral arms like Andromeda's, no sprawling stellar nurseries glowing in color, no eye-catching supernova remnants lighting up its outskirts. It is classified as a Seyfert 1 galaxy, a specific kind of active galactic nucleus that emits intense radiation from its center. On paper, it's just one of countless millions cataloged by astronomers, a grain of cosmic sand in a vast galactic beach. But in this modest-looking galaxy lies something extraordinary. Hidden behind its light years of stars and interstellar gas is a gravitational singularity so powerful, it anchors the entire galaxy. At its heart is the black hole MCG 6-30-15, a name that may seem technical, but behind it is one of the most enigmatic and extreme objects ever observed in astrophysics. Its presence isn't just inferred through the orbits of stars or dust around it. It shouts across the void through X-ray light warped by gravity and stretched by spin. MCG 6-30-15 exists in a relatively isolated pocket of space. The galaxy itself is not part of a dense galactic cluster, which makes it easier for astronomers to observe its central region without interference from nearby galaxies or background noise. That central region, glowing faintly in visible light but roaring in X-rays, tells us that something powerful is happening deep within. And while 130 million light-years may sound distant, cosmically speaking, it's within our observational reach, close enough for telescopes like Chandra and XMM Newton to peer into its heart and analyze the fury within. Its location in Centaurus is symbolic in a way. The constellation, named after the half-human, half-horse creature of mythology, represents duality, strength and intelligence, savagery and thought. Fitting, then, that MCG 6-30-15 resides here, a galaxy containing a black hole that both destroys and illuminates, one that tears matter apart but also gives us one of the clearest views into relativistic extremes. When we look towards Centaurus and the faint smudge of MCG 6-30-15, we're not just seeing light from a galaxy, we're seeing into the past. Because that light, particularly the warped and redshifted X-ray light from the galactic center, has taken over 130 million years to reach us. It began its journey when dinosaurs still roamed the Earth, when continents looked nothing like they do today. And yet, it arrives now, allowing us a glimpse of what happens when gravity spins up to nearly the speed of light. What sets MCG 6-30-15 apart from the countless other black holes scattered across the universe isn't just its mass or its position at the center of a galaxy. It's the speed at which it spins, unimaginably fast, so fast that the very fabric of space around it is dragged into motion. While all rotating black holes twist spacetime to some degree, this one approaches the extreme. Its spin is estimated to be greater than 98% of the speed of light. That's not poetic exaggeration, it's physics on the edge of its limits. This black hole is nearly a perfect example of what theorists call a maximally spinning Kerr black hole. To understand just how fast that is, imagine this: the event horizon, the point of no return, sits just above a singularity rotating so fast that the innermost region of space is dragged along with it. Space doesn't just curve, it spins. That's frame dragging. And in MCG 6-30-15, this dragging of spacetime becomes so intense that it alters everything in its vicinity, including the light escaping from near its edge. But spin alone doesn't make it unique. What really drew attention to this black hole was its X-ray signature, which is unlike anything seen in most other galaxies. When matter falls into a black hole, it doesn't drop straight in. It spirals inward, forming an accretion disk of gas and dust that heats up to millions of degrees. This superheated material emits X-rays before disappearing beyond the event horizon. In MCG 6-30-15, these X-rays are bizarrely warped, not just redshifted or dimmed, but broadened and skewed in a way that screams. Relativistic effects are in full force here. Astronomers first picked up on this strange signature in the early 2000s using space-based X-ray observatories. They noticed a feature in the spectrum of X-rays known as the iron K-alpha line, which should appear as a sharp spike. But instead, it was distorted, flattened on one side and stretched on the other. This indicated that the photons emitting from the inner edge of the accretion disk were being affected by two powerful forces: gravitational redshift and Doppler shifts caused by the disk's high-speed rotation. These effects are so strong, they can only be produced in the immediate vicinity of a rapidly spinning black hole. And that's why MCG 6-30-15 is so special. It's one of the first black holes where this kind of extreme physics has been observed so clearly. It has given us direct, measurable evidence of relativistic warping, a chance to test Einstein's theory of general relativity in one of the most violent environments imaginable. Its light is not a simple flash or a static glow, it is a complex pattern of emissions, pulses, and echoes that reflect the geometry of warped spacetime. This black hole is like a cosmic laboratory, a natural particle accelerator that takes light and matter to their extremes. Its spin, approaching the universal limit, makes it more than just a curiosity. It becomes a fundamental test case for how fast black holes can rotate, how matter behaves near the speed of light, and whether our models of space and time can survive the test of such intensity. And in that strange, warped X-ray spectrum, astronomers find not just anomalies, but answers. Proof that we are observing not just an ordinary black hole, but one of the most extreme spinning objects known to science. MCG 6-30-15 doesn't just spin, it defines what it means for a black hole to spin near the speed of light. And every photon it emits carries with it a story of that intense rotation, of a region where time dilates, gravity rules, and physics is stretched to the breaking point. At the very core of MCG 6-30-15 lies its dark and powerful heart, an active galactic nucleus, or AGN. These are not quiet places. Unlike the calm and orderly solar neighborhoods we're used to, An AGN is a region of cosmic violence, a place where gravity dominates all, and matter is torn apart in a final, furious dance before it is swallowed by a black hole. MCG 6-3015's nucleus is especially turbulent, lit up not by stars or supernovae, but by the furious energy generated as matter spirals into oblivion. This isn't just a quiet black hole lurking silently in the dark. It is actively feeding, devouring surrounding gas, dust, and perhaps even the occasional star. As material falls inward, it doesn't disappear all at once. Instead, it forms a rotating accretion disk that compresses and heats the infalling matter until it glows with intense radiation, especially in the X-ray part of the spectrum. This radiation can outshine the rest of the galaxy combined, making the central region blindingly luminous even though the black hole itself remains invisible. Zooming into this heart, what we find is a kind of gravitational storm. The black hole at the center of MCG 6-30-15 isn't just pulling in material, it's warping the space around it, bending the orbits of nearby particles, distorting the light that tries to escape, and dragging spacetime itself into a spiraling whirlpool. The closer one gets to the black hole, the more intense the warping becomes, until even light cannot maintain a straight path. It's a region where space curves in on itself, time slows down, and every physical law we know is pushed to its limit. In many galaxies, the central black hole is relatively dormant, interacting only subtly with its surroundings. But in MCG 6-30-15, the central engine is very much alive and active. The AGN glows in multiple wavelengths: optical, ultraviolet, and most critically X-rays. The black hole's immense gravitational pull draws the material from across the galaxy. This process is chaotic and highly energetic, and the infalling matter forms shock waves, magnetic turbulence, and high-energy particle interactions that make the AGN an object of intense scientific interest. What's particularly fascinating about this black hole is the extent to which it dominates its surroundings. Within a few light-years of its center, the normal structure of the galaxy seems to break down. Gas clouds don't move in slow orbits. They race around at relativistic speeds, many approaching a significant fraction of the speed of light. This isn't a place of gentle stellar motion, it's a cosmic maelstrom. The black hole itself is estimated to have a mass in the millions of solar masses range, not as massive as the titanic black holes at the centers of quasars, which can be billions of times the mass of our Sun, but still an absolute heavyweight in its own right. And in a galaxy like MCG 6-30-15, that's enough to significantly shape the dynamics of its inner region. Stars, gas, dust, all of it feels the influence of this central monster. Even more fascinating is the structure of the AGN itself. Surrounding the accretion disk is a region called the corona, a hot, diffuse cloud of high-energy particles that is thought to emit much of the observed X-ray radiation. This corona might be shaped by magnetic fields twisted by the spinning black hole, or it might arise from shock waves in the accreting material. It's not yet fully understood, but it plays a crucial role in how the black hole interacts with its surroundings. Further out, the radiation from the AGN affects the interstellar medium of the host galaxy. High-energy X-rays and UV light from the accretion disk ionize the gas around the nucleus, creating enormous regions of ionized material that stretch thousands of light-years into space. This means that even far beyond the immediate vicinity of the black hole, its presence can still be felt, shaping star formation, altering the chemical makeup of the galaxy, and perhaps even regulating its growth over time. Another reason the AGN in MCG 6-30-15 is so intriguing is because it lacks something many other AGNs have: large, powerful jets. In many galaxies with active black holes, material near the event horizon is funneled into narrow jets that shoot out from the poles of the black hole at near-light speeds, often stretching across thousands, or even millions of light-years. These jets are like cosmic fire hoses, pumping energy and matter into the galaxy's outskirts. But in MCG 6-30-15, these jets are either absent or extremely weak. This raises important questions. Why doesn't this black hole produce jets, despite its high spin? Is it a question of orientation? Or is there something fundamentally different about its magnetic field structure or accretion process? This absence of jets makes the black hole even more mysterious. It suggests that spin alone might not be the only factor that determines whether a black hole produces jets. It may also depend on the configuration of the magnetic field in the accretion disk, or the type of material falling into the black hole. Whatever the reason, it makes MCG 6-30-15 stand out even more, an outlier even among extreme outliers. It's also worth considering how astronomers are able to study this AGN in the first place. Unlike visual telescopes that rely on light our eyes can see, observations of MCG 6-30-15 require space-based X-ray telescopes, such as the ESA's XMM Newton and NASA's Chandra X-ray Observatory. Earth's atmosphere blocks X-rays, so to observe the black hole's furious activity, we must go above the sky, beyond weather, beyond air, into orbit. These space observatories collect the high-energy X-rays streaming out from the AGN, allowing scientists to reconstruct what's happening in the central region of the galaxy. And what they see is nothing short of astonishing. The AGN doesn't shine with steady light. It flickers, pulses, and flares, sometimes brightening dramatically over the course of a few hours, only to fade again. These X-ray fluctuations are like seismic tremors in the gravitational field, ripples of activity caused by matter falling inward, colliding, heating, and vanishing. Each pulse is a final scream from particles making their last orbit before being consumed. At this scale, everything feels exaggerated. Time dilates. Distances contract. What would take years to happen in our solar system unfolds in minutes or seconds here. The AGN is a region of fast-forwarded chaos, where the normal pace of the universe is shattered by proximity to the singularity. This proximity gives scientists a unique window into high-energy astrophysics and general relativity, a chance to study how matter behaves when exposed to the most powerful forces nature can muster. And in the very center of all this chaos sits the black hole of MCG 6-30-15. Not merely a passive consumer of matter, but an architect of cosmic structure, an engine of radiation, a master of time and gravity. It defines its host galaxy not just by mass, but by influence, an invisible ruler whose reach extends far beyond its event horizon. Surrounding the black hole at the center of MCG 6-30-15 is one of the most remarkable and violent structures in the universe. Its accretion disk, a cosmic whirlpool of gas, dust, plasma, and magnetic chaos spiraling ever closer to the abyss. This is no ordinary disk. It is a structure shaped by gravity and accelerated by motion, where the simple act of falling transforms matter into radiant energy, and the very laws of physics are dragged to their limits. At first glance, one might imagine this accretion disk as a flat, spinning ring, like Saturn's iconic belts. But in truth, it's a dynamic, turbulent maelstrom. The material that ends up in this disk begins its journey far from the black hole, perhaps drifting interstellar gas, disrupted stars, or even the remnants of larger structures pulled apart by tidal forces. As this material is captured by the black hole's gravitational grip, it starts to spiral inward, forming a rotating disk due to the conservation of angular momentum. As the gas moves closer to the event horizon, gravitational energy is converted into heat and radiation. The closer it gets, the faster it moves. At the outer edge, the material is relatively cool, but as it descends inward, passing through layers of pressure, friction, and magnetic interaction, it heats up to extreme temperatures. By the time it reaches the inner accretion disk, the matter is millions of degrees hot, so hot, in fact, that it emits energy not in visible light, but primarily in X-rays. These X-rays don't just stream out in a uniform glow. They flicker, echo, and shift, depending on what's happening within the disk. Sometimes, a large clump of material might plunge inward and cause a spike in brightness. Other times, magnetic instabilities might create turbulence, which heats some regions more than others. The X-rays become a dynamic portrait of the chaos just outside the event horizon, a radiative ballet of energy being squeezed out of matter before its final plunge. This disk, in the case of MCG 6-30-15, extends incredibly close to the black hole itself, far closer than it could around a non-spinning black hole. This is because the black hole's extreme spin pulls the innermost stable circular orbit, ISCO, closer to the event horizon. For a non-spinning black hole, the ISCO lies at about 3 times the Schwarzschild radius. But for MCG, 6-3015's nearly maximally spinning black hole, this orbit is dragged inward to less than 1.25 times that distance, an incredibly tight spiral, where material schemes just above the point of no return. In this inner region, the gravitational and relativistic effects are at their strongest. The disk's material orbits at nearly the speed of light, and this high velocity causes Doppler effects to become visible in the light it emits. On the side of the disk rotating toward us, light is blue shifted, its wavelength compressed, making it more energetic. On the side rotating away, light is redshifted, stretched out, losing energy. When combined, these effects smear out the sharp X-ray signatures, particularly the iron K-alpha line, into a broadened, skewed shape that only makes sense in the presence of near-light-speed motion and extreme gravity. The disk structure is also affected by magnetic fields. The differential rotation of the gas, where inner regions orbit faster than the outer regions, creates shear forces that twist and stretch magnetic field lines, potentially creating powerful magnetic reconnection events. These can inject sudden bursts of energy into the disk, leading to X-ray flares and variability that telescopes detect as rapid changes in brightness. This activity gives the disk its flickering, heartbeat-like behavior, a kind of electromagnetic pulse that we can observe from across the cosmos. Above and below the accretion disk is the corona, a region of hot, tenuous plasma that plays a key role in producing X-rays. The exact nature of the corona is still debated, but one leading theory suggests it may be powered by the magnetic fields erupting from the disk, similar to solar flares on the Sun, but vastly more energetic. The corona may scatter lower-energy photons from the disk into higher-energy X-rays through a process known as inverse Compton scattering. The result is a brilliant, complex interplay between the cooler disk and the hotter corona, producing a wide range of X-ray energies. But the disk around MCG 6-30-15 is not perfectly flat. Observations hint that the inner regions are warped, likely twisted by the black hole's rapid spin. This twisting comes from a phenomenon known as the Bardeen-Pedersen effect, in which the spin axis of the black hole causes the innermost parts of the disk to align with its rotation, while the outer disk remains tilted. The transition between these two regions leads to a warped structure, where gravitational torques and frame dragging reshape the very geometry of the matter falling in. This warped disk further complicates the picture of X-ray emission. Photons emitted from different regions follow bent trajectories, curved by gravity before they reach our telescopes. Some photons that would otherwise shoot off into space instead loop around the black hole one or more times before escaping, a process called gravitational lensing. This lensing causes us to see parts of the disk that would otherwise be hidden. In some cases, light from the far side of the disk bends around the black hole and appears on the near side, giving a warped, mirrored image that defies common intuition. The brightness of the disk also depends on the inclination angle, the angle at which we, from Earth, view the disk. In the case of MCG 6-30-15, astronomers believe we are seeing the disk at a relatively high inclination, meaning we're not looking directly down onto it, but rather from a slanted angle. This makes the Doppler shifts more pronounced, especially the broadening of the iron line, and gives us a better view of the light-bending effects happening near the event horizon. One of the most remarkable aspects of this accretion disk is that, although it is composed of chaotic, turbulent material, it acts like a natural laboratory, a test zone for the laws of physics under extreme conditions. Every flicker, every pulse of X-rays tells us about what's happening in that last, desperate region before matter crosses into the black hole forever. These signals allow astronomers to backtrack the processes, to decode what's going on just outside the event horizon. And perhaps most profoundly, this accretion disk is the black hole's only voice. The black hole itself emits no light, no signal. But the disk, the swirling sea of doomed matter, is what reveals the monster within. It shines with the energy of destruction, releasing more radiation in a small region than entire galaxies do across hundreds of thousands of light years. It is a self-illuminating death spiral, beautiful in its structure, terrifying in its implications. The accretion disk of MCG 6-30-15 is not merely an accessory to the black hole. It is an active component of the system's physics, a source of intense energy, a canvas of relativistic effects, and a key to unlocking the secrets of black hole spin. Through its light, twisted and stretched, we gain a rare glimpse into a world where gravity dominates, time falters, and even light itself is bent to the will of the spinning void. To truly understand the fury of MCG 6-30-15, we had to look at it with eyes that don't see visible light. Ordinary telescopes, whether ground-based or orbiting, can't perceive the kind of radiation that reveals the secrets of this cosmic predator. Its most revealing signals don't come in the form of glowing stars or picturesque nebulae. They come in X-rays, invisible to the human eye, but vital for uncovering the high-energy processes happening just outside the event horizon. To detect and interpret these signals, we had to turn to two of the most advanced space-based instruments humanity has ever built, the XMM Newton and the Chandra X-ray Observatory. These observatories are not ordinary telescopes. They are orbiting laboratories specifically designed to detect the universe's most energetic and dangerous emissions. X-rays are absorbed by Earth's atmosphere, a life-saving trait for organisms like us, but a frustrating limitation for astronomers. That's why these observatories were launched into space, where they could operate above the protective blanket of the atmosphere and directly capture X-rays streaming from across the cosmos. XMM Newton, the X-ray multi-mirror mission, was launched by the European Space Agency in December 1999. It carries some of the most sensitive X-ray mirrors ever constructed, arranged in a set of nested concentric cylinders, an ingenious design that allows the observatory to focus high-energy X-ray photons using grazing incidence optics. Traditional mirrors don't work at these energies. X-rays simply pass through or are absorbed. But XMM Newton's design enables it to collect and focus them, allowing for detailed spectroscopy, the measurement of light's component energies, to analyze the physical conditions around high-energy cosmic sources. When XMM Newton turned its powerful gaze toward MCG 6-30-15, it detected something astonishing. The X-ray spectrum emitted by the galaxy's active core was not what one would expect from a normal black hole. In particular, the iron K-alpha line, a key spectral signature from iron atoms in the accretion disk, was dramatically broadened and redshifted. This wasn't a subtle feature. It was a loud, undeniable sign that something extreme was happening in the gravitational field of the black hole. The photons being emitted weren't escaping easily. They were being warped, dragged, and sometimes even sent into looping orbits by the fierce curvature of spacetime. Shortly after XMM Newton's revelations, NASA's Chandra X-ray Observatory provided its own perspective. Launched in July 1999, just a few months before XMM Newton, Chandra offers exceptional spatial resolution, the sharpest X-ray imaging of any telescope to date. While XMM Newton excels at collecting large numbers of photons for spectroscopy, Chandra's strength lies in its ability to resolve fine structures in X-ray images. Together, these two observatories form a perfect pair, one optimized for detailed imaging, the other for deep spectral analysis. When Chandra observed MCG 6-30-15, it confirmed and refined the results of XMM Newton. The broad iron line wasn't an observational artifact or a one-time glitch. It was a persistent feature, an imprint of the black hole's fierce gravity and relativistic rotation. The data showed that the disk extended very close to the black hole, closer than what would be possible around a non-spinning black hole. This allowed scientists to infer that the black hole was spinning at greater than 98% of the theoretical maximum, a breathtaking speed, indicating a spin so fast that even time and space begin to stretch under its influence. These observations were a turning point in black hole physics. For the first time, astronomers weren't just theorizing about what might happen near a rapidly spinning black hole. They were measuring it, watching it unfold in real time, photon by photon. The X-ray signatures captured by XMM Newton and Chandra gave direct evidence of relativistic effects predicted by Einstein's general relativity. Effects like gravitational redshift, Doppler broadening, and frame dragging weren't just mathematical curiosities, they were observable facts. But these observatories didn't just reveal that the black hole was spinning fast. They also gave insight into the behavior of the corona, the mysterious, high-energy halo of plasma that sits above the accretion disk. Variations in the X-ray brightness over time, called light curves, showed that the corona could change its shape and position, sometimes collapsing inward, sometimes flaring outward. These fluctuations helped map the inner disk and the structure of the corona, offering a kind of X-ray topography of the region just above the event horizon. Even more compelling was the detection of X-ray reverberation echoes, delayed reflections of X-ray bursts bouncing off different layers of the accretion disk. Like sonar pings in deep space, these echoes allowed astronomers to measure distances and delays on scales of a few gravitational radii, helping them reconstruct the 3D structure of the inner accretion flow. It's as if the black hole was speaking in echoes, and these observatories had finally learned how to listen. Another vital role these observatories played was ruling out alternative explanations. Could the strange broadening of the iron line have been caused by absorption in surrounding gas clouds? Could it be a blending of multiple narrow features rather than one relativistically broadened one? The answer was no. The consistent pattern of the red wing extending far into low energies, down to around 4 keV, was only explainable by relativistic effects near a high-spin black hole. The data from XMM Newton and Chandra matched the predictions of relativistic disk models, especially those governed by the Kerr metric, a mathematical solution for rotating black holes. These missions demonstrated how powerful spectroscopy and timing analysis are when combined. Not only could they detect the signature of fast-spinning gravity wells, but they could also track the changes over time, allowing for dynamic modeling of the black hole's environment. Each observation became a frame in a movie of matter being shredded, heated, and consumed, all orchestrated by the titanic spin of the central black hole. And perhaps most importantly, these observatories helped confirm that MCG 6-30-15 wasn't a fluke. Other galaxies with active nuclei began to show similar features, though not always to the same extreme. MCG 6-30-15 became a benchmark, a Rosetta Stone for understanding what X-ray emissions from a near-maximally spinning black hole should look like. Its signals became templates used to decode other X-ray spectra from across the universe. The combined efforts of XMM Newton and Chandra didn't just observe this black hole, they transformed it into one of the best understood astrophysical laboratories for high-spin black hole behavior. Thanks to their precise instruments and long observation times, we now have an incredibly detailed picture of what happens when matter approaches the edge of physics, when spin reshapes spacetime, and when energy is released on a scale far beyond anything humans have ever created. These space-based telescopes turned the invisible visible. They gave us eyes to watch a black hole spinning at near-light speed, tearing apart matter and twisting the very fabric of the universe. Without them, MCG 6-30-15 would have remained an obscure name in a star catalog. With them, it became a cosmic icon, a black hole not just theorized, but seen, measured, and understood in exquisite, terrifying detail. Among the myriad of cosmic signals that reach us from the distant galaxy MCG 6-30-15, one feature stands out like a fingerprint pressed into the very fabric of light itself, the iron K-alpha line. This spectral line, a signature from iron atoms in the accretion disk, is not just a curiosity, it's a beacon. A silent, yet astonishingly clear indicator that something extraordinary, something extreme, is happening in the space around this black hole. When astronomers first observed this line in the X-ray spectrum of MCG 6-30-15, they immediately knew they were witnessing physics pushed to its edge. To understand what makes the iron K-alpha line so special, we must first understand what it is. In its most basic form, the iron K-alpha line is a fluorescent emission, a narrow spike in the X-ray spectrum that arises when an electron in an iron atom is knocked out of its inner shell, and another electron falls in to take its place. This quantum transition releases a photon with a very specific energy, typically around 6.4 keV, kiloelectronvolts, which is consistent and easily recognizable. In laboratory settings, this line appears as a sharp peak, a clean and narrow feature. But in the environment around MCG 6-3015 central black hole, this line is anything but narrow or clean. Instead, it's smeared, broadened, and skewed into a complex and asymmetric shape. Instead of a neat spike at 6.4 keV, the iron line in MCG 6-30-15 stretches far below and above this value, with a long, flattened red wing that dives as low as 3 keV and a truncated blue edge that rises just above the rest energy. This peculiar shape was the first smoking gun that something profound was occurring in the vicinity of the black hole. The explanation lies in relativistic effects, a combination of Doppler shifts, gravitational redshifts, and light bending that alter the energy and direction of the photons before they ever reach our instruments. The material in the accretion disk is orbiting the black hole at speeds approaching that of light, especially in the inner regions closest to the event horizon. As this iron-rich matter rotates toward us, its emitted photons are blue-shifted, compressed into higher energies. Meanwhile, the material moving away is redshifted, stretching its photon energy to lower frequencies. This Doppler effect creates a bipolar broadening of the line. But that's just the beginning. The truly dramatic distortion comes from gravitational redshift. Near the black hole, the intense curvature of spacetime saps energy from escaping photons. As these photons climb out of the gravitational well, they lose energy, appearing to us as redshifted light. This effect is strongest for photons emitted closest to the black hole, especially from the innermost regions of the disk. These create the extended red wing of the iron line, dipping to much lower energies than should be possible under Newtonian physics. And then there's light bending. In the extreme gravity near the black hole, even photons that would normally head in one direction are curved along warped paths. Some orbit the black hole multiple times before escaping. Others are redirected toward the disk itself, bouncing back and forth in complex trajectories. These warped paths mean we can see parts of the disk that would normally be hidden, particularly the far side of the inner disk. As a result, we receive a blend of emissions from different orbital velocities and gravitational depths, each altering the shape of the iron line. All of these effects, relativistic Doppler shift, gravitational redshift, and light bending, combine to transform a simple, narrow iron K-alpha emission into a distorted, asymmetric profile. The result is what's known as a broad iron line, and it is one of the clearest and most direct signs that we are observing matter in the grip of strong gravity, under the influence of a rapidly spinning black hole. In MCG 6-30-15, the profile of this broad iron line was so distinct, so dramatic, that it couldn't be explained by any ordinary astrophysical mechanism. Early attempts to explain it as an effect of intervening gas, or as multiple narrow lines blended together, fell apart under scrutiny. No combination of ordinary processes could produce the pronounced red wing observed in the spectrum. Only relativistic models could reproduce the shape exactly, particularly those involving a near-maximally spinning curved black hole. In fact, this line profile was one of the key pieces of evidence that led scientists to estimate the black hole's spin at greater than 98% of the speed of light. But it's not just the shape of the line that's informative, it's also the timing. The line varies in brightness over short timescales, suggesting that the emitting region is very close to the black hole, within just a few gravitational radii. This variability tells us that the disk is dynamic, with waves of matter moving in and out, brightening and dimming in response to changes in accretion flow, magnetic turbulence, or coronal activity. The fact that the iron line responds to these changes so rapidly means we're witnessing activity from a region just above the event horizon. One particularly fascinating phenomenon observed in MCG 6-30-15 is reverberation mapping of the iron line. During X-ray flares from the corona, astronomers can track how quickly the iron line responds. The delay between the primary flare and the reflected response in the disk provides a way to measure distances on a scale of just a few light seconds, distances equivalent to tens of kilometers when dealing with such compact objects. It's like using light itself as a ruler, allowing us to map the inner structure of the accretion disk and confirm just how close it extends to the event horizon. This kind of mapping reinforces the conclusion that the disk reaches inward to the innermost stable circular orbit, ISCO, which is pulled dramatically inward in the case of a fast-spinning black hole. For MCG 6-30-15, the ISCO lies just above the event horizon, meaning the iron line is produced in a region where spacetime is not only curved, but actively dragged along by the black hole's rotation. This dragging of spacetime, frame dragging, is a unique relativistic phenomenon that adds yet another layer of distortion to the iron line. As the black hole spins, it pulls space itself into rotation, causing orbits to twist and precess in complex ways. The result? The disk becomes not just a simple ring of matter, but a twisted, spiraling, precessing flow of radiation and particles, all contributing to the smeared, skewed spectral line that we detect from Earth. So what makes the iron K-alpha line so important? It's not just a marker, it's a messenger. A line written in high-energy light that tells us, unambiguously, that we are observing the warping of space and the bending of time near a rotating singularity. It's the closest thing we have to an astronomical Rosetta Stone for strong field gravity. And in MCG 6-30-15, it is one of the strongest, clearest, and most extreme examples ever recorded. Every spike and dip in that line, every shift in its symmetry or energy, is a fingerprint of relativistic processes happening on scales we can scarcely comprehend. It is, in many ways, the heartbeat of the black hole, recorded in X-rays and echoing across 130 million light-years to reach our detectors. And through that heartbeat, we don't just observe a black hole, we feel its pull, we witness its hunger, and we begin to understand its power. In the wild gravitational depths surrounding MCG 6-30-15, light doesn't travel the way it does across calm regions of space. Here, in the neighborhood of a black hole spinning near the speed of light, every photon is shaped by motion, gravity, and warping spacetime. X-rays, which are already high-energy messengers, undergo dramatic changes before they escape this violent arena. These changes are not just random noise. They are relativistic fingerprints, the signatures of redshift and blueshift, two of the clearest demonstrations of Einstein's relativistic universe at play. To understand what redshift and blueshift mean in this context, imagine standing at the edge of a whirlpool. Matter and energy in the accretion disk are spinning incredibly fast, nearly at the speed of light. As parts of the disk rotate toward our line of sight, the motion compresses the wavelengths of light, blueshift, making them appear more energetic. Meanwhile, on the side of the disk rotating away, the wavelengths are stretched out, redshifted, lowering their energy. This is the relativistic Doppler effect. It's the same principle that causes a siren to change pitch as an ambulance speeds past, but in space, the effect applies to light and becomes amplified when the velocities involved approach the speed of light. In MCG 6-30-15, this relativistic Doppler effect is operating on extreme levels. The inner accretion disk spins so fast that the emitted X-rays are significantly blue-shifted on the approaching side and deeply redshifted on the receding side. The result is not just a shifted spectrum, it's an entirely distorted one. A sharp spectral line from, say, iron atoms becomes broad, skewed, and asymmetrical. Observers see a double-peaked shape, where the blue-shifted peak is sharper and higher in energy, and the red-shifted peak is stretched out and less intense. This distortion is further compounded by special relativity's beaming effect, also known as relativistic beaming. As a region of the disk moves toward us at near-light speeds, the light it emits is concentrated, or beam, in our direction. The approaching side appears brighter than it should, while the receding side appears dimmer. This uneven distribution of brightness adds to the asymmetry of the observed spectrum and enhances the observed blue shift even more. What we see, then, is not a balanced emission from a uniform ring, but a lopsided glow, where one side of the disk dominates the view. And then there's the influence of gravitational redshift, a general relativistic effect. Unlike the Doppler shift, which is caused by motion, gravitational redshift is caused by gravity itself. Near a massive object like a black hole, the curvature of spacetime is so severe that it drains energy from photons trying to escape. The deeper a photon is born in the gravitational well, the more energy it loses climbing out, and thus, the longer its wavelength becomes. For X-rays emitted near the black hole's event horizon, especially from the innermost edge of the accretion disk, this redshift can be extreme. High-energy X-rays emitted at 6.4 keV, for example, may arrive at Earth's telescopes at just 4 keV or less, having surrendered much of their original energy to the pull of the black hole. This gravitational redshift works in tandem with the Doppler shifts, and the result is a complex, beautifully chaotic signature. Photons emitted from the inner disk are both redshifted by gravity and red or blue shifted by motion, depending on their trajectory. This produces the broad red wing of the iron line seen in MCG 6-30-15, a portion of the spectrum that stretches far into lower energies, a region that simply cannot be explained by any mechanism other than extreme relativity. The shape and extent of these shifts allows scientists to probe the black hole's environment with incredible precision. By modeling the energy profile of the broadened line, astrophysicists can infer how fast the disk is spinning, how close it extends to the black hole, and even how much space is being dragged along by the black hole's spin. For MCG 6-30-15, these shifts confirm that the disk reaches within 1.2 gravitational radii of the black hole, closer than possible for any non-spinning black hole. This observation alone confirms that the black hole must be spinning at greater than 98% of the speed of light, a truly astonishing result. One of the most powerful demonstrations of these shifts is seen during X-ray flares, sudden bursts of energy emitted from the corona above the disk. When such a flare occurs, the inner disk becomes briefly illuminated, producing a stronger signal and more pronounced relativistic effects. As the X-rays bounce off the disk and echo back toward Earth, we can track the precise timing and energy of the shifts, revealing the changing geometry of the disk in real time. This technique, known as X-ray reverberation mapping, allows scientists to watch the interplay of Doppler and gravitational effects almost like a time-lapse video, one frame per photon. The combination of redshift and blue shift also helps scientists test fundamental physics. The precise shapes of these shifted lines match the predictions of general relativity with extraordinary accuracy. They confirm that gravity does, in fact, warp time and space, and that motion near the speed of light dramatically alters how we perceive energy and direction. MCG 6-30-15 thus becomes a proving ground not just for black hole physics, but for the very fabric of spacetime itself. It's important to note that this shifting of X-rays isn't just a pretty detail. It is essential for understanding how black holes feed, grow, and affect their environments. The redshifted photons come from material spiraling inward, on the brink of being consumed. The blue-shifted photons come from material moving toward us, speeding through space before disappearing forever. These photons carry information about angular momentum, orbital dynamics, and magnetic turbulence in the disk. By studying their energies and patterns, astronomers can map not only the geometry of the disk, but also the physics of accretion, heating, and radiation under extreme conditions. Redshift and blue shift also tell us something more profound, that our perception of time and motion is not universal. In Newtonian mechanics, time flows evenly and space is absolute. But here, in the gravity well of MCG 6-30-15, time slows down, space twists, and the energy of a photon becomes a negotiable quantity, bending to the will of velocity and gravity. The X-rays that reach us carry the memory of these distortions, and in decoding them, we are not merely observing light, we are listening to the warped music of spacetime itself. And so, when telescopes like XMM Newton or Chandra detect those subtle shifts in the X-ray spectrum, they are not just capturing distant echoes. They are reading the dynamic script of an environment where light is bent, time is stretched, and motion scrapes against the very limits of the possible. In MCG 6-30-15, redshift and blue shift are not just technical measurements. They are the language in which the black hole tells its story. To understand the deep and haunting story of MCG 6-30-15, we have to follow the journey of light itself. Not just how it's emitted, or how it moves, but how it struggles. Because around a black hole spinning at nearly the speed of light, even light fights to escape. One of the most remarkable and counterintuitive consequences of Einstein's general theory of relativity is that gravity can stretch light, robbing photons of their energy as they flee the warping depths of spacetime. This phenomenon is known as gravitational redshift, and it plays a central role in the distorted, bleeding X-ray spectrum we observe from MCG 6-30-15. Imagine a single photon, just one packet of light, born in the swirling inner edge of the accretion disk that hugs this black hole's event horizon. It is emitted from an iron atom, heated to millions of degrees, glowing in high-energy X-rays. The photon's journey begins mere kilometers from the black hole's surface, closer than the innermost stable circular orbit, where spacetime is twisted and stretched almost beyond comprehension. To reach us, this photon must climb out of an immense gravitational well, one that bends not only the paths of objects, but the flow of time itself. According to general relativity, gravity isn't a force pulling in the traditional sense. It's the curvature of spacetime, shaped by mass and energy. Near a black hole, spacetime is curved so steeply that light itself follows bent paths. But even more profoundly, as a photon rises out of this curved region, it loses energy. Not because something slows it down, photons always travel at the speed of light, but because their frequency decreases as they gain distance from the gravitational field. Frequency and energy are directly linked. When frequency drops, so does energy. And when energy drops, the light's wavelength increases, it gets stretched, shifted toward the red end of the spectrum. This stretching is gravitational redshift. For photons emitted far from a massive body like a planet or star, the effect is tiny. A photon escaping Earth's gravity loses such a small amount of energy that it's almost impossible to detect without precise instruments. But near a black hole, especially one like MCG 6-30-15, spinning ferociously and pulling spacetime inward, the effect becomes dramatic. Photons emitted close to the event horizon lose a substantial fraction of their energy just to escape. An X-ray photon that began its life at, say, 6.4 keV may arrive at Earth at only 4 keV, or even less, its energy drained by the climb through curved spacetime. This effect is not symmetrical. Photons emitted from the inner accretion disk, the region closest to the black hole, are more redshifted than those from the outer disk. And when these emissions are observed together, the result is a smeared spectral line with a pronounced red wing. This red wing is one of the key diagnostics of gravitational redshift. It cannot be created by ordinary processes like thermal broadening or scattering through gas. Only extreme gravity, strong field gravity, can stretch the photon's spectrum in this way. What's even more fascinating is that the gravitational redshift doesn't just affect the photon's energy, it affects time itself. Observers closer to a massive object experience time more slowly compared to observers further away. This time dilation means that, from our vantage point on Earth, processes occurring near the black hole appear to happen more slowly. If we could watch the inner accretion disk with infinite precision, we would see matter appearing to fall more slowly as it approached the event horizon, and light emitted from those regions would carry this temporal distortion. But unlike the classical redshift caused by an object moving away from us, the Doppler redshift, gravitational redshift depends not on motion, but on position. It's not about where the emitter is going, but how deep it lies in the gravitational well. And in MCG 6-30-15, that well is among the deepest we've ever observed. Its black hole, spinning at over 98% of the speed of light, pulls the very ISCO, the innermost stable circular orbit, within a few gravitational radii of the event horizon. This means that the iron atoms emitting X-rays, and the photons born from them, are operating in an environment where time and energy are warped to extremes. What does this look like in practice? On a graph, the spectral line from iron atoms should be sharp and peaked. But in the data from MCG 6-30-15, that line is broad and lopsided, with a long red tail stretching toward lower energies. This skewed shape is the direct result of gravitational redshift. It's as if the light is bleeding out, losing its vitality, as it climbs up the well of curved spacetime. This broad, redshifted profile also gives us a window into the spin of the black hole. The faster a black hole spins, the closer the accretion disk can orbit before becoming unstable. And the closer the material is to the event horizon, the stronger the gravitational redshift it experiences. The width of the red wing in the iron line profile is therefore not just a visual artifact, it is a measurement of spin, a way to reverse engineer the conditions of the disk. In MCG 6-30-15, the red wing stretches far enough to tell us that the material must be orbiting within 1.2 gravitational radii, only possible if the black hole is spinning nearly at the maximum allowed by the laws of physics. And it's not just iron lines that are affected. The entire X-ray spectrum is influenced by gravitational redshift. Continuum emissions from the disk are dimmed and reddened. Reflected light echoes more slowly, with lower energy, than would be expected in a flat spacetime. Even the coronal flares, bursts of X-rays that illuminate the disk, appear warped in both energy and timing. The entire electromagnetic conversation between the black hole and its environment is filtered through the curved lens of gravitational redshift. For astronomers, this isn't a nuisance, it's a tool. By analyzing how different parts of the spectrum are redshifted, scientists can map the gravitational landscape around the black hole. They can determine how steep the gravitational well is, how deep certain regions lie within it, and how time and space are distorted in those regions. This gives us more than just a picture of the black hole, it gives us a testbed for general relativity, where Einstein's equations are pushed to their most extreme and unforgiving conditions. Gravitational redshift, then, is not just an academic effect. It's a dramatic, observable consequence of the curvature of spacetime. In MCG 6-30-15, it turns a line of iron into a red-wing banner of gravity. It shows us that light can lose a battle against the pull of mass, and that energy is not immune to the reach of spacetime's distortion. It teaches us something profoundly humbling, that even the universe's fastest travelers, photons, must yield to the warping influence of a spinning black hole. That light, the one constant we thought untouchable, bends not only in path but in essence, altered forever by where it was born. And in those altered signals, we read the story of MCG 6-30-15, one photon at a time, one climb through gravity after another. As we continue descending into the extreme physics surrounding MCG 6-30-15, we come upon one of the most eerie and fascinating predictions of general relativity, frame dragging. If gravitational redshift shows how light loses energy while escaping a massive object, frame dragging shows how space and time themselves are twisted by a spinning mass. In the case of a nearly maximally spinning black hole like the one at the center of MCG 6-30-15, this effect is not subtle. It is colossal. It is everywhere. It dominates the very geometry of the region, altering the rules by which matter moves and light travels. In this strange domain, nothing, not even space, can remain still. To grasp frame dragging, we must first let go of the Newtonian notion that space is passive, an empty container through which matter floats. According to Einstein, space and time are not just backgrounds to the cosmic story, they are active participants. Mass and energy tell space how to curve, and space tells matter how to move. But when that mass is not only immense but also spinning, the effect is even more dramatic. The rotating mass drags the very fabric of spacetime along with it, like a spinning spoon stirring thick molasses. This is frame dragging, also known as the Lentz-Thirring effect, after the Austrian physicists who first described it in 1918. It means that in the vicinity of a rotating object, spacetime doesn't stay fixed. Instead, it starts to rotate with the object, as if space itself is caught in the spin. This isn't just a metaphor, it has measurable consequences. A gyroscope placed near a spinning black hole would slowly precess, its axis of rotation shifting in response to the swirling spacetime around it. Even the orbits of particles are affected. They cannot remain in stable, static positions. They must co-rotate, moving in the direction of the black hole's spin whether they want to or not. Near MCG 6-30-15, frame dragging is pushed to the absolute extreme. The black hole is spinning at more than 98% of the speed of light, meaning its angular momentum is close to the maximum allowed by general relativity. In this regime, the dragging of spacetime becomes so powerful that any object, or even light itself, must move in the direction of the spin. There's simply no other option. The region where this occurs is known as the ergosphere. The ergosphere is not the event horizon itself, but a kind of outer shell that surrounds it. Within this zone, stationary existence becomes impossible. Even if you try to hover with a rocket engine at full blast, you cannot stay still relative to the distant stars. Space-time is being dragged forward so fiercely that the only way to remain in place would be to move against the flow of space itself, an impossible feat without faster-than-light propulsion. The only paths available are those that move in the direction of the black hole's rotation. This forced co-rotation is the purest expression of frame dragging. Inside the ergosphere, bizarre things happen. For example, particles can enter, split into two, and one piece can fall into the black hole while the other escapes with more energy than it entered with. This is the Penrose process, a theoretical mechanism by which energy could be extracted from a spinning black hole, made possible only because spacetime itself is rotating. While MCG 6-30-15 hasn't shown strong signs of producing relativistic jets, this kind of energy extraction may still occur in subtler ways, such as heating the disk or launching flares. The dragging of frames also affects the orbits of matter in the accretion disk. In normal Newtonian mechanics, orbits are fixed ellipses or circles. But around a spinning black hole, the orbital planes of particles precess. They slowly twist over time due to the warped spacetime. This leads to complex motions where particles follow wobbling paths, never repeating exactly the same trajectory. The result is a dynamic, turbulent accretion disk whose inner edge constantly shifts and reshapes itself. This precession affects more than just gas. It also leaves imprints on X-ray emissions, especially the iron K-alpha line discussed earlier. Because the disk geometry is changing under the influence of frame dragging, the shape and timing of the X-ray signals fluctuate. We can observe these variations from Earth, using instruments like XMM Newton and Chandra. The result is not just a static picture of a spinning black hole, it is a movie, a dynamic unfolding of spacetime in motion. And yet, frame dragging doesn't just warp space, it warps time. Near a spinning black hole, the flow of time itself is twisted into a spiral. Clocks closer to the black hole tick more slowly than those farther away, but when the black hole is rotating, this time dilation becomes directional. Time slows differently depending on whether you move with or against the spin. In a sense, the black hole imposes a preferred direction on the flow of time, violating the symmetry we take for granted in most of the universe. This has led to tantalizing speculation. Could extreme frame dragging create closed time-like curves, loops in spacetime where time itself forms a circle? In theory, yes. In the precise solutions of Einstein's equations known as the Coherence, which describes spinning black holes, there exist paths through spacetime that allow an object to return to its own past. Of course, these paths lie deep inside the event horizon, likely unreachable from the outside universe. But the mathematics suggests that a spinning black hole like MCG 6-30-15 doesn't just distort space and stretch time, it may twist time into self-intersecting knots. In practice, we observe the consequences of frame dragging in more grounded ways. The inner edge of the accretion disk is pulled closer to the event horizon, making it hotter, brighter, and more dynamic. The disk precesses. Light bends. Particles spiral inward in complicated paths. The very shape of the event horizon becomes oblate, flattened at the poles and bulging at the equator, because of the rotational energy. This spinning spacetime acts like a cosmic tornado, spinning everything within its reach. It's easy to forget how radical this idea is. That space and time are not fixed, but malleable. That the spin of a distant black hole can alter the geometry of reality in such a way that time and motion become twisted. But around MCG 6-30-15, this is not a theory, it's observable fact. The patterns we see in its X-rays, the dynamics of its accretion disk, the evidence of precession and energy distortion, all of it points to a region of space where frame dragging is not just happening, it is dominant. In that sense, MCG 6-30-15 is more than just a powerful black hole. It is a spacetime engine, a rotating mass so intense and so fast that it takes the stage of reality itself and spins it into a vortex. To stand near it, not that anyone could, would be to feel time pull and twist, to see space swirl beneath your feet. Light would bend. Matter would orbit not in circles, but in spirals that never repeat. And space wouldn't be the empty void we know. It would be an ocean caught in a whirlpool, dragged by a force that acts not on things, but on the very rules by which things exist. Frame dragging makes black holes like MCG 6-30-15 more than just gravitational sinks. It makes them sculptors of spacetime, entities that rewrite the structure of the universe around them, imposing spin not only on matter but on the void itself. In the chaotic gravitational ballet that unfolds around a black hole like MCG 6-30-15, not every orbit is created equal. There is a line, an invisible, yet unbreakable boundary, where stability ends and inevitability begins. This line is known as the innermost stable circular orbit, or ISCO, and it marks the closest distance at which matter can orbit the black hole without spiraling inward toward destruction. The ISCO is a threshold, a frontier, and in the case of spinning black holes like MCG 6-30-15, it's one that's far closer to the abyss than anywhere else in the universe. In classical Newtonian gravity, orbits can exist at any distance from a massive object, as long as the orbital speed balances the gravitational pull. There's no unstable orbit, just a continuum of possible paths. But general relativity changes the rules. Near a massive, compact object like a black hole, the fabric of spacetime becomes so warped that only a certain range of circular orbits are dynamically stable. Inside the ISCO, any slight perturbation will send an orbiting object plunging inward, unable to resist the black hole's grip. Even light can be trapped in unstable circular paths just outside the event horizon, known as photon spheres. For a non-spinning, or Schwarzschild black hole, the ISCO lies at 6 gravitational radii from the center. That's 6 times the Schwarzschild radius, or 3 times the diameter of the event horizon. For black holes like this, any material orbiting inside that radius will spiral inward in a matter of milliseconds, doomed to cross the event horizon and vanish forever. But MCG 6-30-15's black hole is not Schwarzschild. It's a near-maximally spinning Kerr black hole, rotating at over 98% of the speed of light. And spin changes everything. In Einstein's theory, a black hole's rotation pulls the ISCO inward, allowing stable orbits to exist much closer to the event horizon. The faster the spin, the smaller the ISCO. In fact, for a black hole spinning at the maximum rate allowed by general relativity, what's called an extremal Kerr black hole, the ISCO is located at just 1 gravitational radius, just above the event horizon itself. In MCG 6-30-15, evidence from the distorted X-ray spectrum, especially the extremely broad and redshifted iron K-alpha line, suggests that the ISCO lies at 1.2 gravitational radii, closer than almost any black hole we've ever observed. This means that matter in the accretion disk is orbiting only a hair's breadth from the edge of the event horizon, deep in the grip of the black hole's gravity, where spacetime is dragged into rotation and light barely escapes. This proximity to the event horizon has profound consequences. First, it means that the material in the inner accretion disk is moving at relativistic velocities, close to the speed of light. The gravitational and Doppler redshifts it experiences are enormous. It also means that this material is subject to extreme tidal forces, stretching and compressing as it whips around the black hole in a fiery whirlpool. The friction and magnetic turbulence in this region convert gravitational energy into heat and light, producing high-energy X-rays that we detect from Earth. But there's more. The closeness of the ISCO to the event horizon in a Kerr black hole means that the black hole can be a more efficient engine. As matter falls in, the amount of energy it can radiate before crossing the horizon depends on how deep it can orbit before falling in. For a non-spinning black hole, the efficiency of this process is about 6%, meaning 6% of the infalling matter's mass energy is radiated as light and heat. For a maximally spinning Kerr black hole, This efficiency rises to nearly 42%. That's higher than any nuclear process known. The ISCO's position thus directly affects the black hole's radiative power. This helps explain why MCG 6-30-15 shines so brightly in X-rays, despite being 130 million light-years away. Its inner disk, extending right down to the ISCO at 1.2 gravitational radii, is an incredibly energetic region, dense, fast, hot, and luminous. The radiation from this region not only powers the iron K-alpha emission, but also generates variable light echoes, Doppler-Broaden lines, and a steady stream of photons that encode the physics of the strong field regime. But the ISCO is more than a limit for accretion, it is also a clock. The orbital period of matter at the ISCO depends on the black hole's mass and spin. For stellar mass black holes, this can be just milliseconds. For supermassive black holes like the one in MCG 6-30-15, it's on the order of minutes to hours. Observing quasi-periodic oscillations QPOs in X-ray light curves, repeating flickers of X-ray intensity, gives astronomers a potential way to measure the ISCO's radius indirectly, by linking the observed timing to the orbital dynamics of matter near this innermost edge. It's a remarkable interplay of theory and observation. Einstein's equations tell us where the ISCO should be, given the mass and spin of the black hole. The distorted X-ray spectrum tells us how close the disk actually comes. And the timing of flickering light tells us how fast material is orbiting. All three lines of evidence for MCG 6-30-15 converge to one incredible conclusion. The ISCO is closer to the black hole than almost anywhere else we've observed in the universe, and it proves beyond doubt that we are looking into a region governed by extreme relativistic effects. Interestingly, the ISCO also determines how the black hole evolves. As matter falls in from the accretion disk, it transfers angular momentum to the black hole, gradually spinning it up. But once the ISCO reaches its innermost limit, the black hole approaches the so-called Thorne limit, a theoretical boundary at about 99.8% the speed of light, beyond which no further spin-up can occur without violating known physics. MCG 6-30-15 spin is dangerously close to this limit, suggesting that it may be as fast as a black hole can get under the laws of general relativity. And so, the ISCO becomes not just a feature of orbital mechanics, it becomes a cosmic yardstick. It tells us how fast the black hole is spinning. It tells us how efficiently it converts matter into light. It determines how hot and bright the disk becomes. And it defines the final stable path before all motion collapses inward, falling past the event horizon into silence. Standing at the ISCO, in theory, would be like standing at the edge of a cosmic cliff. Behind you, the disk is turbulent but safe, stable orbits, manageable radiation, survivable gravity. Ahead of you, everything falls. No orbit is possible. No light can return. The ISCO is the dividing line between stability and doom, between physics we can observe and regions we can only speculate about. In MCG 6-30-15, that line lies closer to the edge of the black hole than almost anywhere else we've seen, reminding us just how extreme the universe can become when mass, motion, and spacetime conspire to twist reality itself. To say that the black hole in MCG 6-30-15 is spinning fast is a stunning understatement. It's not just rotating. It's pirouetting on the very edge of physics. According to the best estimates derived from decades of X-ray observations and detailed spectral modeling, this black hole is spinning at over 98% of the speed of light, a dizzying, almost unimaginable rate of rotation. And it's entirely possible that the spin is even faster than that, nearing the theoretical upper limit that a black hole can sustain under general relativity. Let's break down what that actually means. In physics, we describe a black hole's spin using a dimensionless parameter called the spin parameter or Kerr parameter, usually denoted by the symbol A. This value ranges from 0 to 1. A value of 0 describes a non-rotating Schwarzschild black hole. A value of 1 describes a maximally rotating Kerr black hole, one spinning at the absolute speed limit imposed by Einstein's theory of general relativity. For MCG 6-30-15, the measured spin parameter is greater than 0.98. That means this black hole is rotating at 98% of its theoretical maximum, which translates into frame dragging so severe, spacetime itself is being pulled around with it at nearly light speed. The event horizon isn't a quiet, spherical surface, it's an oblate, spinning vortex, warping everything around it. But why are we so confident in this number? The answer lies in the X-rays. The inner edge of the accretion disk, as we've discussed, orbits close to the black hole, at a distance determined by the spin. The faster the black hole spins, the closer this inner edge, the ISCO, can be. And the closer the disk extends to the event horizon, the more extreme the gravitational redshift and relativistic Doppler effects that impact the X-rays emitted from the disk. These changes are imprinted most clearly in the iron K-alpha line, a spectral signature that originates from iron atoms bombarded by high-energy radiation in the disk. In MCG 6-30-15, this iron line is extraordinarily broadened and skewed. Its red wing stretches far into lower energies, implying that the light is coming from very close to the event horizon, in a region of intense gravitational warping. The shape and extent of this line can be modeled using the mathematics of general relativity, and when those models are fit to the observations, they consistently point to a spin parameter of a greater than or equal to 0.98. This isn't just a one-off measurement. Multiple independent observations from telescopes like XM and Newton and Chandra have confirmed it. They have observed the distorted X-ray spectrum, measured the shape of the iron line, and analyzed time lags and X-ray echoes bouncing off different regions of the disk, what's known as reverberation mapping. These time delays, caused by light taking longer to travel out from deeper gravitational wells, also indicate that the inner disk is brushing right up against the ISCO, which can only happen if the black hole is spinning very close to maximally. So how fast is this in everyday terms? Well, black holes don't spin in quite the same way as planets or stars do. They don't have a solid surface or an atmosphere. Instead, their spin refers to the angular momentum of the spacetime geometry itself. But if we try to visualize it, the equator of a maximally spinning supermassive black hole could be moving at over 1 billion kilometers per hour, or nearly 300,000 kilometers per second, basically right at the speed of light. That's enough to circle the Earth 7 times in a single second. And because MCG 6-3015's black hole is spinning at over 98% of this rate, it's effectively one of the fastest spinning objects in the known universe. But there's an even deeper layer to this. Such an extreme spin means the black hole has had a very specific and violent evolutionary history. It couldn't have started out this way. Black holes are born from the collapse of massive stars, but a single stellar collapse doesn't typically result in a near-maximal spin. Instead, this black hole must have gained angular momentum over time, most likely by accreting matter from its surroundings in a consistent direction for millions or billions of years. That is, it didn't just fall into spin, it was spun up, relentlessly, by feeding on a swirling, directional inflow of gas and dust. And the fact that it maintained this spin, despite the chaotic, turbulent environment of the accretion disk, speaks to the efficiency of its feeding process. Some models suggest that magnetic fields, disk viscosity, and even jet launching mechanisms can regulate spin over long periods of time. But in the case of MCG 6-30-15, those forces seem to have cooperated to push the spin ever higher, perhaps to the point of hovering just below the theoretical ceiling of A=1. It's worth mentioning that spinning this fast also amplifies some of the more exotic effects we associate with black holes. The Ergosphere, the region just outside the event horizon where frame dragging is unavoidable, becomes more prominent. The ISCO moves in closer, making the accretion disk hotter and more luminous. The potential for energy extraction increases, and the gravitational environment becomes so extreme that even light is twisted into bent and looping paths. We're not just looking at a fast-rotating object, we're looking at a factory for high-energy physics, a place where space-time itself is in turmoil. What would happen if a black hole like this spun even faster? General relativity places a strict upper limit on spin, because beyond a spin parameter of A=1, a rotating black hole would become naked, exposing its singularity to the universe. This violates what's known as the cosmic censorship conjecture, a principle suggesting that nature hides singularities behind event horizons. If a black hole were to spin faster than this limit, the event horizon would collapse, leaving behind a region where known physics breaks down entirely. No observations of such objects have ever been confirmed. An MCG 6-30-15, while flirting with that limit, remains within the bounds of a curved black hole. Yet the idea that we are observing a black hole approaching the limit of what general relativity allows is not just thrilling, it's scientifically invaluable. MCG 6-30-15 becomes not only an object of interest, but a laboratory for testing fundamental physics. If we ever saw a deviation from the predicted behavior of such a high-spin black hole, it could suggest new physics, perhaps from string theory, quantum gravity, or dimensions beyond our own. For now, all signs suggest MCG 6-3015's black hole is an almost perfect curved black hole, a real-life manifestation of Einstein's most elegant solution. Its spin is not just a number, it's a force, a shaping influence, a sculptor of spacetime. And in that spin, encoded in every stretched photon and every flicker of X-ray light, is a message: the universe is not static. It turns. It spirals. It dances, sometimes at nearly the speed of light. As we drift deeper into the gravitational theater surrounding MCG 6-30-15, it becomes harder to speak in straight lines, because light itself can't travel in them. Around a black hole spinning at near light speed, light doesn't obey the Euclidean instincts we trust in daily life. It bends. It loops. It curves in perfect arcs. And in doing so, it paints a reality that is warped and twisted, where what we see is never quite where it is, and what exists might never be seen at all. This is the realm of gravitational lensing, a phenomenon predicted by Einstein's general relativity and spectacularly verified by observations across the universe. It tells us that mass doesn't just pull on matter, it bends the very paths light takes. When light from a distant star or galaxy passes near a massive object, such as another galaxy or black hole, it doesn't continue in a straight line. Instead, it curves along the warped fabric of spacetime, like a marble rolling along a deformed rubber sheet. In normal astronomical lensing, such as when a galaxy clusters lenses a more distant quasar, this effect leads to multiple images, arcs, or even Einstein rings. But near MCG 6-30-15, gravitational lensing becomes something else entirely. This isn't a soft nudge to a beam of light traveling past. This is a violent gravitational grip, so intense that light is pulled into spirals, redirected around the black hole in entire revolutions, and in some cases captured entirely, orbiting several times before escaping or vanishing forever. The intense light bending around MCG 6-30-15 causes three major observational distortions, and each reveals a piece of the space-time puzzle unfolding near this cosmic vortex. First is image distortion. The accretion disk around MCG 6-30-15 is a thin, glowing ring of hot gas, blazing in X-rays. But what we see isn't the disk as it is. Due to the black hole's immense gravity, the side of the disk behind the black hole is bent up and over, so that we can see it even when it should be hidden. Light from the far side of the disk is curved around the black hole and aimed directly toward us. The result is a surreal image. The top of the disk shows both the near side and the ghost of the far side, curved into view by the black hole's lensing power. It creates a glowing halo effect, what's known as the photon ring. Even more disorienting, there's a region near the black hole where photons can orbit in closed loops. This photon sphere, which for a non-spinning black hole lies at 1.5 times the Schwarzschild radius, becomes smaller and more complex for a fast-spinning curved black hole. Here, light can circle the black hole multiple times, sometimes making several orbits before finally escaping to the universe or succumbing to the pull of the event horizon. When this light finally reaches us, it carries with it a time-delayed, warp signature, often contributing to the X-ray echoes and spectral tails we observe. Every extra loop adds a subtle twist to the data, a faint echo of the same region, seen from different gravitational angles. Second is energy distortion. As light moves through curved spacetime, its energy can change. If it climbs out of the gravitational well, it becomes redshifted, losing energy, as previously discussed. But if it moves in the direction of motion, or falls inward slightly before escaping, it can be blue-shifted, gaining energy due to the motion of the disk. The result is a spectrum that's stretched and skewed in ways that can only be explained by light moving through a warped landscape. For example, the iron K-alpha line isn't just broadened because of velocity or temperature. It's warped because of the way light bends and shifts in energy around the black hole. The line's asymmetrical shape, its sharp blue peak and smeared red tail, is the fingerprint of light bending through spinning spacetime. On one side of the disk, matter is moving toward us at relativistic speeds, beaming light forward. This contributes to the sharp, high-energy edge of the spectrum. On the other side, the light is moving away, redshifted and stretched, contributing to the elongated tail. And all of this is being reshaped by the curved paths light takes to reach our detectors. Third is time distortion. Light doesn't just travel in curved paths near a black hole. It takes longer to get anywhere. This leads to a phenomenon known as Shapiro delay, where signals from deep within the gravitational well are delayed compared to those from farther out. This delay is encoded in the light echoes we observe, brief flashes of X-rays that bounce off different parts of the disk, reaching Earth at staggered intervals depending on the paths they took through warped spacetime. It's like a cosmic sonar system. By measuring how long different signals take to arrive, we can map the geometry of space itself, tracing the contours of the black hole's gravitational field. In MCG 6-30-15, these time distortions are especially severe. The region where the X-rays are emitted is extremely close to the event horizon, meaning the light must climb a steep gravitational gradient just to escape. The result is that light emitted from different parts of the disk, at the same moment in the black hole's frame, can arrive at our telescopes seconds or even minutes apart, depending on how deeply it originated. This delay encodes a kind of temporal fingerprint, revealing not just where the light came from, but how spacetime stretched or compressed around it during its journey. It's a mind-bending truth. When we observe MCG 6-30-15, we are not seeing a simple object in space. We are seeing a complex hologram of twisted light, a multi-layered reflection of warped geometry. Some of the light we see is old, delayed by its looping path. Some of it is duplicated, refracted from the backside of the disk. Some of it is smeared across time and energy, shifted and stretched by motion and gravity. And at the heart of it all is the black hole, silent and invisible, manipulating light like a puppet master, pulling on the strings of photons, twisting space so tightly that the very concept of straight becomes meaningless. Our eyes, even armed with space telescopes, can barely keep up. What we see is a flattened, distorted simulacrum, layered with illusions. But within those illusions lie the truths of gravity. That spacetime bends, light can be delayed and reshaped, and the image of the universe itself can be a kind of gravitational hallucination. We often imagine black holes as devourers of matter. But around MCG 6-30-15, we see that they also devour the rules of vision. They do not just eat light, they twist its journey, bend its direction, and recraft its meaning. A spinning black hole does not merely consume, it repaints the cosmos, using light as its brush, and gravity as its hand. There is a boundary in the universe beyond which nothing, no signal, no particle, no flicker of light, can ever return. It is not a surface in the traditional sense, not a wall, or a shell you can touch. It is a one-way membrane in the fabric of reality, an edge woven into spacetime itself. This is the event horizon, and around the black hole at the heart of MCG 6-30-15, it is more than a point of no return. It is a warped, spinning threshold, contorted by the black hole's extreme angular momentum. In its simplest form, the event horizon is the radius at which the escape velocity equals the speed of light. For a non-spinning black hole, this horizon is perfectly spherical, and its radius is given by the Schwarzschild solution, R equals 2 gm/c superscript 2, where g is the gravitational constant, m is the black hole's mass, and c is the speed of light. Anything that crosses this boundary, matter, light, information, cannot get out again. Its destiny is sealed. But MCG 6-3015's black hole is anything but simple. It spins at over 98% of the speed of light, which means it isn't described by the Schwarzschild metric, but rather by the more complex Kerr solution, the solution to Einstein's field equations that accounts for rotation. In the Kerr geometry, the event horizon changes dramatically. First, it is no longer a perfect sphere. The immense rotational energy causes it to flatten at the poles and bulge at the equator, much like how Earth itself is slightly flattened due to its own spin, but on a far more extreme scale. The faster the spin, the more distorted the horizon becomes. For near-maximal spins, like the one in MCG 6-30-15, the event horizon becomes oblate, pulled outwards at the equator due to the overwhelming angular momentum, and dragging spacetime around with it. But the distortions aren't just physical in appearance. They're fundamental to how space and time behave near the horizon. In the Schwarzschild case, the event horizon is static. In the Kerr case, it rotates. Not in a conventional way, like a planet spinning on an axis, but in a relativistic sense. The very spacetime around the event horizon is caught in the black hole's spin. This results in the frame dragging we previously discussed being strongest at the horizon itself, where no object, not even a photon, can resist being pulled into the spin. This leads to a dramatic structure, the black hole's ergosphere, which lies just outside the event horizon. In this region, no object can remain stationary. Spacetime itself is swirling so fast that everything, matter, light, magnetic fields, is compelled to co-rotate. You could fire a rocket in the opposite direction at full power, and still find yourself slowly spiraling forward. The event horizon marks the inner edge of this region, the point where even moving at the speed of light can no longer help you escape. Near MCG 6-30-15, this zone is exaggerated. The spin is so extreme that the ergosphere stretches far out from the horizon, forming a thick, rotational envelope where spacetime is violently twisted. Within this space, the rules of motion and light are fundamentally altered. It's here that strange processes like the Penrose mechanism may occur, where energy can be extracted from the black hole by splitting particles and allowing one to fall into the hole while the other escapes, carrying away energy stolen from the black hole's spin. But once past the event horizon proper, this contorted, rotating shell, all paths lead inward. There are no stable orbits, no static positions, no exit strategies. It's not just a place where escape is difficult. It is where escape is impossible. The light cones, the diagrams that map all the possible future directions a particle can move, tilt inward completely. They point only toward the singularity. From our perspective outside, any object crossing the horizon appears to slow down, freeze, and redshift into invisibility. But from the object's own perspective, it crosses the boundary in finite time, plummeting inward to a fate unknown. For spinning black holes like MCG 6-3015's, the event horizon also depends on direction. The distance from the singularity to the event horizon is smaller along the direction of spin, and larger perpendicular to it. This causes the shape of the horizon to be asymmetric, and it even alters how close matter can orbit before falling in. It tightens the space in which matter can survive, compressing the boundary of stability, and sharpening the effects of gravity and time dilation. And remarkably, the spin also determines how close you can get to the singularity itself. In a Schwarzschild black hole, the singularity is a point, a single spot of infinite density. In a Kerr black hole, it is not a point, but a ring. This ring's singularity lies within the event horizon, formed by the rotation of mass. And unlike in the non-spinning case, there exists a region inside the horizon, called the Cauchy horizon, where, in theory, time and space may switch roles again, and where even weirder possibilities emerge, time loops, alternate universes, paths that escape the singularity. These are mathematical curiosities at the edge of physics, and whether they exist in nature remains a subject of debate. But their theoretical existence underscores just how deeply spin affects the very nature of a black hole. At the cosmic scale of MCG 6-30-15, these are not just abstract concepts. They are encoded in the light we see. The distorted X-ray spectra, the warped iron lines, the bent echoes, the relativistic time lags, all are shaped by the proximity of matter to this rapidly spinning horizon. Every photon that escapes the black hole's grip tells a story, of close brushes with the boundary, of paths altered by gravity, of time stretched and twisted near the edge of forever. It is difficult to express just how alien the event horizon of MCG 6-30-15 truly is. If you could observe it directly, you would not see a calm, black sphere. You would see a blurred, glowing ring, surrounded by a halo of refracted light from the warped accretion disk, and distorted by extreme gravitational lensing. The horizon itself would appear larger on one side, thanks to Doppler beaming, and would shimmer with the echoes of infalling matter. From some angles, it might look like a hole torn in the sky, from others, like a pulsating ring of fire. And no matter how close you hovered outside it, crossing it would end any hope of returning information to the universe. This is what the event horizon means in MCG 6-30-15, a border not just of visibility, but of causality. It is the edge where space turns inward, where time becomes one-directional toward oblivion, and where the laws of physics, at least as we currently understand them, cease to offer answers. It is not merely the border of a black hole. It is the horizon of what we can know. And yet, for all its violent gravitational grip and its almost unimaginably fast spin, MCG 6-30-15 is missing one of the most dramatic and iconic features often associated with such cosmic monsters, a relativistic jet. In many active galaxies, especially those with spinning supermassive black holes, astronomers observe twin jets of matter being blasted out from the poles of the black hole at nearly the speed of light. These jets are made of charged particles, accelerated by powerful magnetic fields, and they can extend for thousands or even millions of light-years into intergalactic space. They glow in radio, X-rays, and sometimes even gamma rays, creating vast lobes that outshine the entire galaxy in which they reside. These jets are not mere astrophysical fireworks. They are profound expressions of the black hole's influence. They regulate star formation in galaxies, inject energy into the intergalactic medium, and act as cosmic beacons, letting us observe quasars and radio galaxies from billions of years in the past. Their existence is not just an after effect, it's central to understanding how black holes interact with their environments. And this is what makes MCG 6-30-15 so puzzling. It has all the ingredients for powerful jet production, a supermassive black hole, spinning at more than 98% the speed of light, surrounded by a highly active accretion disk that glows brightly in X-rays. The spin itself is especially relevant. One of the leading theories for jet formation, known as the Blandford's-Nagic mechanism, proposes that the rotational energy of a black hole can be extracted via strong magnetic fields threading through the event horizon. This energy is then funneled into collimated jets along the black hole's rotational axis. In this framework, a fast-spinning black hole is a perfect jet engine. And yet MCG 6-30-15 doesn't seem to have one. No large-scale relativistic jet has ever been detected from this galaxy. Radio observations reveal no bright lobes, no twin jets piercing the intergalactic darkness. High-resolution X-ray data from Chandra and XMM Newton show no extended structures suggestive of outflowing matter. There are no gamma-ray flares, no large-scale shocks, no bow waves moving through intergalactic gas. This black hole, for all its immense spin, is eerily silent in the directions we most expect to hear it roar. This silence raises compelling questions. Why doesn't this black hole produce jets? What's different about its environment, its disk, its magnetic fields, or even the very nature of its spin? One possibility lies in the geometry of the accretion disk. In many jet-producing systems, the accretion disk is thick and geometrically puffed up, possibly forming a magnetically choked corona or an advection-dominated flow. This structure may help collimate magnetic field lines and facilitate jet production. In MCG 6-30-15, however, the disk appears to be thin and radiatively efficient, a classic Shakur-Sunyaev disk, radiating energy away as light rather than building up the pressure and magnetic twist required for powerful outflows. Another possibility concerns the alignment of spin and accretion. For jets to form effectively, the black hole's spin axis and the angular momentum of the accreting matter need to be well aligned. If the disk is misaligned, tilted at a significant angle to the spin axis, then it may not produce the symmetrical conditions necessary to launch jets. While some warped disks still produce jets, an extreme misalignment could suppress or destabilize jet formation entirely. Then there is the issue of magnetic flux. Recent simulations of black hole accretion suggest that a threshold of magnetic field strength is needed to initiate and sustain relativistic jets. These magnetically arrested disks, MADs, accumulate large-scale poloidal magnetic fields that become dynamically important, allowing the extraction of rotational energy from the black hole via the Blandford's-Najek process. If MCG 6-3015's disk simply doesn't have sufficient magnetic threading, it might lack the structure to launch jets, no matter how fast the black hole is spinning. It's also possible that small-scale jets are being launched, but they're weak or not collimated enough to be detected. Microquasars and other low-luminosity AGNs sometimes display failed or short jets, jets that don't break through the surrounding material, or that dissipate before traveling far from the galactic core. In MCG 6-30-15, any jet activity could be hidden in the noise, or swamped by other emissions in the X-ray spectrum. And then, most intriguingly, there's the possibility that we are witnessing a black hole in transition, either between phases of activity or in a relatively quiet mode of accretion. AGNs are not static. They can flicker on and off over millions of years. A black hole that lacks a jet today might have one in the distant past or future. In this view, MCG 6-30-15 is simply in a low jet state, with all the physical machinery in place but the trigger not yet pulled. Yet, despite the absence of jets, the black hole is still an engine of tremendous power. It emits intense X-rays, warps spacetime at its core, and provides one of the most extreme known tests of relativistic physics. In some ways, its lack of jets makes it an even more useful object of study. By stripping away the enormous energies and structural complexities associated with jet formation, we can better isolate and understand the accretion process itself, and the influence of spin and disk physics without the confounding influence of massive outflows. It may also reveal something more profound about the diversity of black hole behavior. Not all fast-spinning black holes act the same. Spin may be a necessary condition for jet formation, but not a sufficient one. Environment, disk alignment, magnetic topology, and temporal phase all seem to play crucial roles. MCG 6-30-15 may sit at the threshold of jet potential, close to the edge of becoming a radio-loud AGN, yet held back by conditions that keep its energy bottled up. So here it is, a black hole spinning nearly at the speed of light, its gravity sculpting the shape of light itself, yet no relativistic lances pierce the sky. Instead, it shines silently in X-rays, whispering its story through spectral lines and echoes of distorted light. It is a paradox in motion, a tornado of spacetime without a storm, a cosmic dynamo without a jet, a beacon of gravity's extremes that refuses to shout. And in that silence, there may be hidden answers, about what it takes to create a jet, about how spin interacts with its surroundings, and about how even the most powerful objects in the universe can sometimes keep their fury folded inward, unseen. The story of MCG 6-30-15 is told most eloquently in its light, or rather, in the distortions of that light. Among the many spectral features emitted from its accretion disk, one stands out like a cosmic fingerprint, the iron K-alpha line. But in this galaxy, that line does not behave as one would expect from normal stellar processes. It is not crisp, not narrow, not symmetric. Instead, it is broadened, blurred, and strangely skewed, its shape twisted in ways that can only be explained by the most extreme laws of nature, by relativity itself. And this broad iron line has become a powerful witness, whispering the secrets of what's happening at the very brink of the black hole's event horizon. To understand the mystery, we must first understand the origin of this line. The iron K-alpha line is produced when iron atoms in the accretion disk, superheated and highly ionized, are bombarded by high-energy X-rays. This bombardment kicks out inner shell electrons from the iron atoms. When outer electrons drop down to fill these vacancies, they emit photons at very specific energies, in this case, around 6.4 keV for neutral iron. This emission line should appear sharp and narrow, like a well-defined spike in the X-ray spectrum. But in MCG 6-30-15, that's not what we see. Instead of a sharp spike, we observe a broad asymmetric trough. The line is stretched, spread, and sloped heavily toward lower energies. There is a distinctive red wing that extends well below the expected 6.4 keV, and a blue edge that rises sharply and then cuts off. This line is not just broadened, in the traditional sense, it is distorted beyond any explanation that doesn't invoke Einstein's general relativity. And the degree of that distortion provides a window into what is happening near the black hole's edge. Why does this happen? The first distortion comes from Doppler broadening. As the accretion disk rotates rapidly, the side moving toward us emits photons that are blue-shifted, their energy is boosted by the motion. The side moving away emits photons that are redshifted, their energy is lowered. This alone would make a symmetric double-horn profile, a red peak and a blue peak. But MCG 6-30-15's line isn't symmetric, which tells us there's more at work. That brings in gravitational redshift. Light emitted close to the black hole has to climb out of an intense gravitational well. In doing so, it loses energy, stretching to longer wavelengths. The deeper into the gravity well the light originates, the more redshifted it becomes. This accounts for the long red wing seen in the spectrum. Photons emitted from the innermost regions of the accretion disk, near or at the innermost stable circular orbit, ISCO, are stretched heavily, creating a tail of emission far below the expected 6.4 keV. It's not that these photons started at low energies, it's that they've been pulled down in energy by the black hole's grip. Now add in the effects of light bending. As we saw earlier, photons near the black hole don't travel in straight lines. Many of the photons we detect don't come directly at us. They're lensed, looped, or deflected by gravity. Some photons that were initially aimed away from us get curved into our line of sight. Others make multiple orbits around the black hole before escaping. This lensing warps the image of the disk and blends the emission from different regions, smoothing out and blending the line profile, making it broader and more complex. Finally, and perhaps most crucially, comes relativistic beaming and time dilation. The material in the inner accretion disk is moving at a significant fraction of the speed of light. On the approaching side of the disk, the motion compresses the light in our direction, making it brighter and more energetic. On the receding side, light is stretched and dimmed. The net effect is that the blue side of the line appears boosted and sharp, while the red side is smeared and extended, creating the characteristic skewed shape seen in MCG 6-30-15. Together, these effects form a composite picture, a broad, asymmetric, and relativistically deformed iron line. Its exact shape, and especially how far the red wing extends, gives us crucial information about the inner radius of the accretion disk. In MCG 6-30-15, the red wing plunges to such low energies that it implies the disk is emitting X-rays from a region very close to the event horizon, closer than would be possible unless the black hole was spinning near its maximum rate. This is why the broad iron line is considered smoking gun evidence of the black hole's spin. The extent of the red wing corresponds to the distance between the black hole's center and the ISCO. The faster the black hole spins, the smaller the ISCO becomes. For a non-spinning black hole, the ISCO lies at about 6 gravitational radii, 6 gm/c superscript 2. For a black hole spinning at near light speed, the ISCO drops to just over 1 gravitational radius. The iron line in MCG 6-30-15 suggests that we are seeing X-rays emitted from less than 2 gravitational radii, something that can only occur if the black hole is spinning faster than 98% of the theoretical maximum. This line has become more than just a feature, it's a tool. X-ray astronomers use models of disk emission under relativistic conditions to fit the observed iron line and derive parameters like spin, inclination angle, disk ionization, and inner disk radius. These models are complex, accounting for not just the motion of the matter but the full curvature of spacetime. The more data we collect, the better we can fine-tune these models, and MCG 6-30-15 has provided one of the most consistent and compelling matches to extreme relativistic broadening seen in any active galactic nucleus. But the line is also a mystery, because it shows us what we don't fully understand. Some variations in the line over time suggest fluctuations in the accretion disk, changes in the corona, or shifting magnetic fields. In some observations, the line is even more extended, in others it retreats. These dynamic behaviors hint at complex, time-dependent processes very close to the black hole, possibly even instabilities in the disk or coronal flares that momentarily change the X-ray illumination. There are also unanswered questions about the iron itself. Why is the iron line so dominant in some AGNs but nearly absent in others? Why does MCG 6-30-15, in particular, show such a strong and persistent feature? Is it a matter of elemental abundance? Disk temperature? Viewing angle? Or is it simply that this galaxy gives us a rare, unobstructed view into the heart of relativistic space? Whatever the answers may be, the iron K-alpha line in MCG 6-30-15 stands as one of the most dramatic confirmations of Einstein's predictions. It is a natural laboratory for testing general relativity under conditions that can never be reproduced on Earth. And it offers something profoundly poetic, a spectral echo from atoms on the edge of oblivion, emitting one final burst of light before falling into the unknown. In the deep silence of space, the universe whispers in echoes. And around the black hole in MCG 6-30-15, those echoes aren't sound, they're light. More precisely, they are X-ray echoes, delayed flashes of radiation that carry the timing of a heartbeat coming from the edge of physics itself. This phenomenon is known as X-ray reverberation, and it's one of the most powerful tools we have for mapping the unseen regions near a black hole, where light curves, time dilates, and matter blurs into energy. X-ray reverberation is fundamentally about timing. Imagine an intense burst of X-rays being emitted from a compact, energetic region above the black hole's accretion disk. This region is called the corona, and it's where high-energy processes generate primary X-ray radiation. These X-rays shoot out in all directions. Some travel directly to Earth, reaching our X-ray observatories like XMM Newton and Chandra almost instantly. But some of them travel downward, striking the accretion disk and interacting with the hot gas there. These interactions generate reflected X-rays, often modified by the properties of the disk, its composition, temperature, motion, and gravitational environment. These reflected X-rays then also travel to Earth, but because they took a longer path, their arrival is delayed. This delay, the light echo, holds a precise timestamp of how long it took the X-rays to bounce off the disk. By measuring the time difference between the direct X-ray signal and the reflected one, astronomers can estimate distances on a cosmic scale with remarkable accuracy, down to a few gravitational radii from the black hole. It's like sonar, but for curved spacetime. In the case of MCG 6-30-15, the echoes are not only present, they're incredibly short in delay, on the order of tens to hundreds of milliseconds. That's astonishing when you consider the galaxy is 130 million light-years away. Such brief delays mean that the region reflecting the X-rays is extremely close to the black hole, just a few gravitational radii above the event horizon. It confirms what other clues have suggested. The inner disk of MCG 6-30-15 extends right down to the very edge of the ISCO, the innermost stable circular orbit, and that we are observing reverberations from matter on the brink of falling into the black hole. But it gets more profound. By separating the X-ray signal into different energy bands, scientists can analyze how the delays differ across the spectrum. For instance, higher energy X-rays may arrive sooner or later than lower energy ones depending on the height of the corona and the geometry of the disk. This allows for energy-dependent reverberation mapping, which reveals the vertical structure of the system. It shows us not just how far the inner edge of the disk lies from the black hole, but also how tall or compact the corona might be. The shorter the delay between the primary and reflected signal, the closer the corona must be to the disk, and to the black hole itself. In MCG 6-30-15, this mapping has revealed a low, compact corona, often no more than a few gravitational radii in height. That places it in the intense gravitational field of the black hole, where both gravitational redshift and light bending become extreme. The X-rays it emits are warped in energy and bent in path, many of them illuminating the disk from above in a tightly focused beam. This geometry explains the strong reflected signatures we see, like the iron K-alpha line, and amplifies the relativistic effects that shape them. Even more intriguing is that these reverberation delays change with time. Over hours or days, observations have recorded fluctuations in the delay profiles, suggesting that the corona itself is moving, expanding, or contracting. This paints a picture of a dynamic, shifting environment, where magnetic reconnection events or bursts of infalling matter may cause the corona to flare, rise, or collapse. Each time this happens, the light echoes adjust, the delay shifts, the spectrum reshapes, and the heartbeat of the black hole changes rhythm. There is also a kind of rhythm and phase to these echoes. Certain energy bands respond faster or slower depending on where in the disk they were reflected from. The reverberation mapping technique takes advantage of this by producing lag energy plots, graphs that show how different X-ray energies are delayed compared to a reference band. In MCG 6-30-15, these plots often show clear, energy-dependent structures that line up with predictions from relativistic disk models. These are not just flickers, they are gravitationally encoded time signatures, as if the black hole is playing a musical score written in light. What makes this even more groundbreaking is that this technique allows astronomers to probe regions of spacetime that are otherwise unreachable. Traditional imaging, optical or even radio, cannot resolve the incredibly small scales involved here. We are talking about regions spanning only a few times the size of the black hole itself. No telescope could ever resolve such features in a galaxy so distant. But with X-ray reverberation, we can achieve a kind of temporal resolution that bypasses the limits of spatial resolution. We can map, in real time, the flickering pulse of matter orbiting near the speed of light, buffeted by gravity and time. And again, MCG 6-30-15 is an ideal target for this technique. Its high spin pulls the disk very close to the event horizon, shortening the path between corona and disk, which enhances the echo effect. Its bright X-ray output provides enough photons for precise timing, and its relatively unobstructed view, free from heavy absorption or complex jet interference, makes it a clean laboratory to study these effects in isolation. In a broader context, X-ray reverberation mapping is changing the way we understand black holes. It's being used on stellar mass black holes and X-ray binaries, on quasars billions of light-years away, and on dozens of Seyfert galaxies like MCG 6-30-15. It's becoming a standard tool for spin measurement, disk mapping, and understanding corona behavior. And as future telescopes like Athena and Lynx come online, with even better timing precision and photon collection capabilities, the resolution of these cosmic echoes will become even sharper. Eventually, this may allow us to see variations over time, catching the movement of orbiting hotspots in the disk, mapping their paths as they spiral inward, and maybe even tracking their precession, the slow wobble of orbits predicted by frame dragging. These would be real-time observations of general relativity in action, seen not in images, but in pulses of light. MCG 6-30-15, then, is more than a black hole. It is a cosmic bell, and the echoes that ring from its accretion disk are not random, they are precise, gravitationally tuned signals from deep within warped spacetime. With every echo that reaches our detectors, we are listening to the shape of gravity, the flow of matter, and the very heartbeat of a spinning singularity. Close to the event horizon of MCG 6-30-15's black hole, where the laws of physics stretch and twist under the strain of gravity, the accretion disk doesn't behave like a calm, flat whirlpool of infalling matter. Instead, the intense spin of the black hole, the near-light-speed rotation of a mass millions of times greater than our Sun, distorts the very structure of the disk, bending and warping it in ways that defy our everyday notions of geometry. This is not a stable platform of rotating gas. It's a warped, spiraling sheet of fire, twisted by relativistic effects, frame dragging, and gravity on the edge of collapse. In classical physics, when gas and dust fall into a gravitational well like a star or a black hole, the resulting disk tends to lie in a flat plane, perpendicular to the object's spin axis. It's a simple, elegant structure that arises from angular momentum conservation, similar to how planets orbit in the same general plane around the Sun. But the black hole in MCG 6-30-15 doesn't follow classical rules. It exists in a Kerr geometry, a spacetime twisted by rapid spin. When matter orbits this kind of black hole, it no longer experiences gravity as a simple inward pull. Instead, the spinning black hole drags spacetime around with it, an effect known as frame dragging. This means that the very fabric of the universe around the black hole is swirling, and anything within that region, including the accretion disk, is forced to rotate and twist along with the spacetime itself. This effect gives rise to one of the strangest and most beautiful phenomena predicted by general relativity, the Bardeen-Pedersen effect. When the angular momentum of the accretion disk is not aligned with the spin axis of the black hole, which is often the case when gas falls in from different directions or due to previous galactic mergers, a misalignment develops. The outer parts of the disk may orbit in one direction, but as you move inward closer to the black hole where frame dragging becomes stronger, the orbital planes start to precess, to slowly rotate like a spinning top wobbling under an external force. As this precession continues, a competition emerges. Viscosity within the disk tries to keep it together and coherent, but the black hole's spin exerts differential twisting, a torque that changes with distance from the center. The result is a dramatic warping of the disk, where the inner region eventually aligns with the black hole's equatorial plane due to strong relativistic effects, while the outer disk retains its original tilt. This creates a transition zone, a warped region where the disk bends from one orientation to another. It's not smooth or gentle. It's a dynamic, constantly adjusting region of extreme shear, where matter is being violently twisted, heated, and stirred. In MCG 6-30-15, this warped inner structure likely extends across a few to tens of gravitational radii, a place where every inch of the disk experiences different physics depending on its proximity to the black hole's grip. This warping isn't just a theoretical curiosity, it directly affects what we observe. First, it alters the illumination pattern from the corona. The X-ray producing region hovers above the disk, like a flickering light bulb above a rippling mirror. A flat disk would reflect that light in predictable ways, but a warped disk reflects it unevenly. Some regions of the disk may catch more light than others depending on the curvature, and some might cast shadows or focus the radiation into tight beams. This non-uniform reflection changes the brightness and shape of spectral features like the iron K-alpha line, introducing additional complexities into the profile and its variations over time. Second, a warped disk causes variable light echoes. As we saw with reverberation mapping, the timing between primary and reflected X-rays is key to understanding the disk structure. But if the disk is warped, those delays change not just radially, with distance from the black hole, but azimuthally, with angle around the disk, since the height and orientation of reflecting surfaces vary. This leads to echoes that arrive out of sync, evidence that the disk structure is more like a spiral staircase than a flat carousel. Third, a warped disk affects the polarization of X-ray light. As X-rays scatter off the disk surface, their electric field orientation changes. In a flat disk, this polarization pattern is symmetrical and predictable. But a warped, twisted disk breaks that symmetry, leading to polarization signatures that betray the disk's complex shape. Future X-ray polarimetry missions may be able to detect these signatures, offering direct observational proof of the disk's warping. And finally, warping may help explain why no strong jet is present in MCG 6-30-15. In jet-producing black holes, alignment between the spin axis and the inner disk appears crucial for launching a stable, collimated outflow. A warped inner disk might disrupt the magnetic fields required to extract rotational energy via the Blandford's-Najek mechanism. It could also cause energy to be diffused or ejected in non-collimated, chaotic bursts, never forming a steady jet. So the very twist of the disk may be the reason why this black hole, despite its incredible spin, remains eerily silent in the radio spectrum. One of the most fascinating consequences of disk warping is its possible precession over time. If the inner warped region rotates, it could lead to quasi-periodic oscillations (QPOs) in the X-ray light curve, rhythmic flickers that reflect the movement of hot spots, shadows, and gravitational wells rotating near the black hole. Some of these QPOs have been tentatively observed in MCG 6-30-15, hinting that we may be watching the real-time wobble of a warped disk, an echo of relativistic instability, caught in the act. So this disk, far from being a simple structure, is a flexing, twisting, and precessing dynamo. It is the engine of the galaxy's central power, but it is not a stable engine. It ripples like a sheet of silk caught in a cyclone. It warps and realigns, its gas pulled by tidal forces, stretched by frame dragging, compressed by gravity, and irradiated by the corona above. And in that warping lies a deeper beauty, the realization that we are not just watching matter fall. We are watching space itself being sculpted, bent into curves and spirals under the influence of a spinning point of infinite density. The disk is not passive, it is a participant in the drama of relativity, a surface on which the choreography of gravity and motion plays out in light and time. What if time isn't as steady, as absolute, or as reliable as we assume? What if, near certain places in the universe, time itself begins to blur, stretch, or even turn in upon itself? Around MCG 6-30-15, where the black hole spins at over 98% the speed of light and twists spacetime like a whirlpool in a storm, this is no longer the stuff of science fiction. It's physics. And it opens the door to a chilling yet awe-inspiring possibility, that near this cosmic monster, the rules of time begin to crack, perhaps even allowing for the theoretical foundation of a black hole time machine. To explore this, we must first revisit what it means for a black hole to spin. A non-spinning black hole is simple in its terrifying elegance. It pulls everything inward, and nothing can escape once it crosses the event horizon. But when a black hole spins, it brings a new dimension to the table. It drags spacetime along with it. This is frame dragging. But frame dragging doesn't just twist space, it also twists time. In Einstein's theory of general relativity, space and time are not separate entities. They are parts of the same unified fabric, spacetime. Near a massive object, spacetime curves. Near a rotating massive object, spacetime spirals. Around a rapidly spinning black hole like MCG 6-30-15, this spiraling becomes extreme. The fabric of spacetime doesn't just dip, it rotates. If you were to try and remain stationary near such a black hole, you'd find it impossible. The very space you occupy is being whirled around the black hole, like leaves caught in a whirlpool. Even light must orbit in the direction of the black hole's spin, unable to remain still. This effect is most dramatic within a region called the Ergosphere, a kind of temporal halo that envelopes the event horizon of a spinning black hole. Inside the Ergosphere, no object can remain motionless with respect to distant stars. Everything is forced to move in the direction of the black hole's rotation, because space-time itself is rotating. You can still escape from the Ergosphere, unlike from the event horizon, but you can't resist the drag of time itself being twisted. This is where things become speculative and profound. The math of spinning black holes, described by the Kerr metric, allows for some unusual and deeply counterintuitive solutions. One of them involves the idea of closed time-like curves, CTCs. These are paths through spacetime that loop back on themselves, not in space, but in time. In theory, an object following a CTC could return to its own past. This is not imagination. This is a legitimate solution to Einstein's equations, at least under very specific and idealized conditions. In the context of a Kerr black hole, if one were to dive deep enough into the geometry, past the event horizon and into regions no traveler could survive, it is mathematically possible to trace a path that brings you back to your starting point in time. In essence, the extreme curvature of spacetime near a rapidly rotating black hole could, in theory, create a kind of natural time loop. Now, there are many caveats. First, this path would lie within the inner structure of the black hole, beyond the inner horizon, a region likely unstable and plagued by quantum effects that break classical general relativity. Second, the intense tidal forces and radiation near this region would almost certainly destroy any traveler or signal. Third, such time loops violate causality and raise paradoxes, the grandfather paradox, for instance, that no physicist has yet resolved in a satisfying way. And finally, many believe that quantum gravity, when fully understood, will eliminate such exotic features from physical reality, much like how quantum effects stabilize classical singularities. But we can't ignore what the equations tell us. Around MCG 6-30-15, where the spin is extreme and the gravitational well is steep, we are as close to these theoretical boundaries as nature allows. Even if actual time travel remains impossible, the time distortion near such a black hole is very real. To an outside observer, a clock orbiting near the ISCO, just above the event horizon, would appear to tick slower and slower. Time, for the orbiting matter, dilates. Seconds for an infalling particle might correspond to minutes, hours, or even days for a distant observer. If you were to hover close to the black hole and look outward, you would see the universe speeding up. Stars would spin faster, galaxies would whirl, and cosmic history would unfold at high speed. You would be in the future, simply by being closer to the gravitational well. This is not science fiction, it's measurable. X-ray reverberation, line broadening, and variability all indicate that matter near the event horizon is undergoing time dilation. In the language of physics, we are not just observing a black hole spin, we are observing time itself being sculpted by rotation. Some theorists even speculate whether energy extraction mechanisms, like the Penrose process, could harness this twisting of time. In such scenarios, particles could enter the ergosphere, split into two, and one escapes with more energy than the original particle had, essentially stealing rotational energy from the black hole by navigating these warped paths through twisted spacetime. In doing so, these particles would not only extract energy, they would be interacting with the geometry of time itself. The philosophical implications are staggering. In MCG 6-30-15, we are not simply watching matter fall into a gravitational abyss. We are witnessing a natural experiment where time behaves differently depending on where you are, how fast you're moving, and how deep you are into the spacetime whirlpool. This black hole spins so fast that it becomes a laboratory for testing the very nature of time, how it stretches, how it bends, and how it might even loop. It's unlikely that MCG 6-30-15 harbors usable time loops. But the fact that it even brushes against such possibilities tells us how close we are to the outermost limits of what reality can permit. This black hole is not just extreme, it's a reminder that time, the most familiar dimension we know, is not absolute. It is malleable. It is warped by gravity. And near a black hole like this one, it can begin to behave in ways that challenge the very foundation of causality itself. Around MCG 6-30-15, time ticks differently. Events unfold more slowly the deeper they fall. And in the limit, right on the edge of the event horizon, time seems to stop altogether, at least from our vantage point. That singularity isn't just a place where gravity becomes infinite. It's a boundary where time and space cease to behave independently, and where the universe itself whispers of things we still cannot fully grasp. In a very real sense, MCG 6-30-15 is a time machine, not in the science fiction sense of leaping across centuries, but in the more profound sense of revealing how fragile and strange the nature of time truly is when placed under the stress of gravity's deepest well. For over a century, Albert Einstein's theory of general relativity has stood as one of the greatest triumphs in science, an elegant mathematical framework describing how mass and energy shape the very fabric of spacetime. It has passed test after test, from the bending of starlight during solar eclipses to the orbit of Mercury and the detection of gravitational waves. But the true strength of any theory lies in how it performs under extreme conditions, in environments where spacetime itself becomes violently distorted. And perhaps nowhere in the observable universe is a better testbed for this than MCG 6-30-15, a galaxy whose central black hole spins with such ferocity. It creates a natural laboratory for the most intense and unforgiving trials of Einstein's theory ever witnessed. What makes MCG 6-30-15 so valuable to physicists isn't just that it contains a black hole. It's that this particular black hole exists in a state of maximal extremity. Its spin rate, estimated at more than 98% of the speed of light, means that the effects of frame dragging, light bending, and time dilation around it are operating at nearly the theoretical maximum allowed by general relativity. And in this environment, relativistic effects aren't small corrections, they are the dominant physics. The first and most striking confirmation of general relativity comes from the iron K-alpha emission line we've discussed before. In most astrophysical systems, this line appears as a narrow spike around 6.4 keV. But in MCG 6-30-15, the line is dramatically broadened, its profile bent and skewed in a way that matches precisely what general relativity predicts for light emitted near a rapidly spinning black hole. The degree of asymmetry and the extent of the red wing in the line's profile align with theoretical models that take into account both Doppler shifting from fast-moving plasma and gravitational redshift from the warped spacetime near the black hole. No Newtonian physics can account for this. No classical gravity theory produces this spectral shape. Only Einstein's equations, solved for a rotating Kerr black hole, generate the correct predictions. And the match between theory and observation is not vague or approximate, it is quantitative. The iron line's shape and timing can be simulated with relativistic ray tracing models, and when applied to MCG 6-30-15, they reproduce the observed spectrum with astonishing fidelity. That's not just a visual resemblance, it's a triumph of relativistic prediction. Beyond the iron line, MCG 6-30-15 also provides a natural test of reverberation mapping techniques that rely on the precise timing of X-ray echoes. The gravitational delays between direct X-ray emission and its reflection from different parts of the accretion disk reveal a relativistic environment where time itself flows differently. These delays are short, milliseconds to seconds, and they change depending on energy, just as general relativity predicts when photons are emitted or reflected from within a strongly curved spacetime. Again, the match between observation and prediction supports the idea that Einstein's theory holds even under the crushing curvature near a spinning singularity. The fact that we can use relativistic disk reflection models to map the inner disk radius, the corona's height, and the black hole's spin with such consistency is a further demonstration that general relativity doesn't just survive in strong fields, it thrives. But there's more. MCG 6-30-15 is also helping to test general relativity's prediction of the innermost stable circular orbit, ISCO. According to Einstein's theory, stable orbits around the black hole can only exist down to a certain radius. Within that, orbits decay and matter plunges into the black hole. For a non-spinning black hole, the ISCO lies at 6 gravitational radii. But for a maximally spinning Kerr black hole, it shrinks to just 1 gravitational radius. In MCG 6-30-15, the observed iron line and timing data imply that matter is emitting X-rays from just 1.3 to 2 gravitational radii away from the singularity. This is only possible if the ISCO has shrunk, which in turn is only possible if general relativity's predictions for high-spin Kerr geometry are correct. These are not trivial confirmations. They tell us something profound. Einstein's equations continue to work even where spacetime is most violently curved, where tidal forces stretch matter into plasma, and where time and space can no longer be cleanly separated. They hold up not just in the weak field of Earth or the Sun, but in the heart of a galaxy where energy density and gravitational gradients are off the charts. Moreover, MCG 6-30-15 may offer insights into the transition point between classical gravity and quantum gravity. General relativity is a classical theory, it doesn't incorporate quantum mechanics. Yet, near a spinning black hole's event horizon, the densities and energies become so extreme that quantum effects should begin to matter. If general relativity were to break down anywhere, it would be here. So far, it hasn't. But the precision measurements being made from this galaxy's black hole may one day help us identify small deviations, hints of new physics that extend or modify Einstein's model. In fact, one of the ultimate goals of modern astrophysics is to use black holes like MCG 6-30-15 to test alternative theories of gravity. Some models predict slightly different behavior in the ISCO. Others predict changes in how light is bent, or in how fast frame dragging occurs. By comparing ultra-high-resolution observational data to the predictions of these theories, scientists can rule out models that don't fit. So far, none have surpassed general relativity, but the hunt continues. Even more tantalizing is the possibility of testing the cosmic censorship conjecture, a principle in relativity that says singularities are always hidden behind event horizons. If a black hole were to spin too fast, the horizon might disappear, exposing the singularity and violating cosmic censorship. In MCG 6-30-15, the black hole's spin is right on the edge of this limit. By precisely measuring how the ISCO behaves and how X-rays are emitted from close to the horizon, astronomers can test whether nature respects this conjecture or whether the equations allow for more exotic, naked singularities. Every photon from MCG 6-30-15, then, is a data point in this grand experiment, a probe sent from the heart of relativistic gravity. And unlike particle accelerators on Earth, which can only test gravity in very weak fields, this black hole allows us to observe gravity in its most extreme, unshielded form. This galaxy is not just an astrophysical curiosity. It is a cosmic laboratory, 130 million light-years away, where space and time are pushed to their absolute limits, and where Einstein's legacy is continually challenged, and so far, continually vindicated. In every warped spectral line, every delayed echo, and every curved path of light, general relativity stands tall, as though the black hole itself is engraving Einstein's equations into the fabric of spacetime with each rotation. Measuring the spin of a black hole, an object from which not even light can escape, might seem like an impossible feat. After all, black holes don't emit light directly. They don't have surfaces we can observe or features we can track. But in systems like MCG 6-30-15, where the black hole is surrounded by a luminous accretion disk of infalling matter, scientists have found an ingenious way to measure the unmeasurable. And it all comes down to analyzing the light from matter dancing on the edge of oblivion. The method at the heart of this effort is called X-ray spectroscopy. It's the study of the energies of X-ray photons emitted from the accretion disk. These photons carry information about where they came from and what happened to them along the way, especially how they were affected by the black hole's gravity and motion. By carefully studying their energies, scientists can reverse engineer the conditions near the black hole and estimate its spin. But not just any X-rays will do. The key lies in a very special spectral feature known as the iron K-alpha emission line, a signature from iron atoms in the accretion disk that fluoresce when bombarded by high-energy photons from the corona above the disk. Under normal conditions, this iron line appears as a sharp spike at 6.4 keV. But near a black hole, this line doesn't stay sharp or simple. It becomes broadened, flattened, and skewed, stretched across a range of energies in a distinctly asymmetric shape. This is where relativistic effects come in. Matter in the inner accretion disk orbits at incredible speeds, sometimes more than half the speed of light. On the side of the disk rotating toward us, the motion compresses the light waves, blue shifting them to higher energies. On the receding side, the light is redshifted, stretched to lower energies. This is the relativistic Doppler effect in action, and it creates a double peak structure in the iron line profile. But that's not the whole story. Gravity plays its part too. The immense gravitational field of the black hole pulls on the escaping light, stealing energy from it in the form of gravitational redshift. Photons emitted closer to the black hole lose more energy as they climb out of its gravitational well, causing their observed energies to shift further to the red. The result is a long, extended redwing in the iron line spectrum, one of the clearest indicators of extreme relativistic effects. Now here's the crucial point. The shape of this broad and iron line depends on how close the inner edge of the accretion disk gets to the black hole. And that inner edge is determined by the black hole's spin. For a non-spinning black hole, the innermost stable circular orbit, ISCO, lies at 6 gravitational radii. But as the spin increases, the ISCO moves inward. For a maximally spinning Kerr black hole, the ISCO is just 1 gravitational radius from the event horizon. So if the iron line has an especially long red tail, that suggests that matter is emitting light from very close to the black hole, and that, in turn, implies a high spin. This is exactly what we see in MCG 6-30-15. The iron line's red wing extends down to energies as low as 3 keV, meaning the light is coming from within 2 gravitational radii of the black hole. Only a black hole spinning at over 98% the speed of light could pull the disk in so close and still allow stable orbits. This is how the spin is measured, by fitting theoretical models of disk reflection to the observed spectrum, and adjusting the spin parameter until the model and the data match. These theoretical models are based on general relativity, and use complex relativistic ray tracing techniques to simulate how light would travel in the warped spacetime near a spinning black hole. They account for Doppler boosting, gravitational redshift, light bending, and the inclination of the disk relative to Earth. By comparing these synthetic spectra to the real data collected by X-ray observatories like XM Newton, Chandra, Suzaku, and NuStar, scientists can extract precise values for the spin. It's worth noting that this method is extremely sensitive to instrument resolution and signal-to-noise ratio. Observations require long integration times and high photon counts to clearly define the line profile. But MCG 6-30-15 is an ideal candidate. It's a Seyfert 1 galaxy, meaning its central engine is oriented in a way that allows us to view the inner accretion disk relatively unobscured. It's also bright in X-rays, producing enough iron line photons for precise analysis. There's another layer of confirmation: time-resolved spectroscopy. By examining how the iron line profile changes over time, say, during flares or dimming events, astronomers can see the effects of different regions of the disk lighting up. This temporal behavior helps cross-check the spin measurements and refine estimates of disk structure and corona height. There is also a second, complementary technique called the continuum fitting method, mostly used for stellar mass black holes and X-ray binaries. It involves modeling the thermal spectrum of the accretion disk's X-ray emission. But for supermassive black holes like MCG 6-30-15, the iron line method is more effective, because their thermal emission peaks in the ultraviolet, not easily observable with current telescopes. Some have proposed adding polarimetry to the mix. X-ray polarimetry can reveal the direction and degree of light polarization, which is affected by relativistic motion and magnetic fields near the black hole. In the future, missions like IXP, Imaging X-ray Polarimetry Explorer, may provide additional constraints on the geometry of the inner disk and help further confirm spin estimates. The takeaway is this: we can't see the black hole in the traditional sense. But by watching how light behaves around it, how it shifts, bends, delays, and spreads, we can determine not only the black hole's mass, but its angular momentum. And because black hole spin affects everything from disk structure to jet formation to energy extraction, knowing this parameter is key to understanding black holes not just as objects, but as cosmic engines. MCG 6-3015's black hole stands out as one of the best measured spinning black holes in the universe. Its iron line spectrum has been modeled extensively. Its echoes have been timed. Its spin has been constrained by multiple instruments over 2 decades. And the verdict is clear: this black hole is spinning at the very edge of physics, offering a perfect arena for testing our deepest theories, and perhaps one day, uncovering new ones. The spin of a black hole is not just a number. It is a defining trait that shapes the very nature of its environment, its behavior, and its long-term evolution. In fact, once a black hole forms, only 3 measurable properties remain: mass, electric charge, and spin, and for astrophysical black holes, charge is effectively zero. That leaves mass and spin as the primary levers of influence. But spin, in particular, has far-reaching consequences. Around a black hole like the one in MCG 6-30-15, which spins at more than 98% the speed of light, everything, from how matter falls in, to how light escapes, to how energy is released, is profoundly affected. Spin determines not just what a black hole is, but how it acts upon the universe around it. First, let's begin with how spin affects the process of accretion, the feeding of the black hole. When matter spirals into a black hole, it doesn't fall straight in. Angular momentum causes it to form a disk, a hot, swirling maelstrom of gas and radiation. But how close this disk can get before plunging into the event horizon depends on spin. As we've discussed, a non-spinning black hole has an innermost stable circular orbit, ISCO, at 6 gravitational radii, while a maximally spinning black hole allows orbits as close as 1 gravitational radius. That's a game changer. The closer matter can spiral and before crossing the point of no return, the more gravitational energy can be converted into radiation. The infalling matter loses energy as it spirals inward, and this energy is radiated away, primarily as X-rays. For a non-spinning black hole, about 6% of the rest mass of the accreted matter is converted into radiation. For a rapidly spinning black hole like MCG 6-30-15, this radiative efficiency can reach up to 42%. That's an astonishing figure, far more efficient than any nuclear reactor, any fusion process in the stars. Spin transforms the black hole from a passive sinkhole into an engine of cosmic luminosity. This higher efficiency means a fast-spinning black hole shines brighter for every gram of matter it devours. That's part of why active galactic nuclei, AGN, like MCG 6-30-15 can outshine their entire host galaxies. It's not just that they're feeding, it's that their spin makes them voracious and efficient. But spin doesn't just dictate how much energy is radiated. It also determines how energy can be extracted from the black hole itself. This brings us to the Penrose process, a theoretical mechanism by which energy can be extracted from a rotating black hole. Within the Ergosphere, the twisted region of spacetime outside the event horizon, a particle can split in two, with one piece falling into the black hole and the other escaping with more energy than the original. This excess energy comes directly from the black hole's rotational momentum. The black hole slows down slightly, and the escaping particle gains a boost. This is energy extraction from spin. Even more powerful is the Blandford's-Najek process, which posits that magnetic fields threading through the black hole's event horizon can tap into the rotational energy of the black hole. This process may be the engine behind the relativistic jets that shoot out from many black holes, narrow beams of plasma moving at nearly the speed of light, powered by twisted magnetic fields and the spin of the black hole itself. The faster the black hole spins, the more energy is available to launch and sustain these jets. Interestingly, MCG 6-30-15 doesn't show strong evidence of such jets, despite its extreme spin. This raises questions. Is something preventing the magnetic field configuration needed for the Blandford's-Najek mechanism? Is the warped inner disk misaligned in a way that disrupts jet formation? These are mysteries we still grapple with. But in other systems, there is strong evidence that spin correlates with jet power, making spin a key ingredient in a black hole's ability to impact its host galaxy. And that brings us to another consequence of spin: feedback. Black holes don't just consume, they influence. The radiation and winds they emit can push on surrounding gas, regulate star formation, and sculpt galactic evolution. A spinning black hole with high radiative efficiency and strong feedback can limit the growth of its own galaxy, clearing out gas that would otherwise collapse into new stars. This is one reason why massive galaxies often have quiet centers. Their central black holes, once active, heated and ejected the gas, shutting down future star formation. Over cosmic time, this interplay between black hole activity and galaxy evolution becomes a cosmic dance. The black hole feeds, grows, and spins. Its spin determines how bright it shines and how powerful its outflows become. Those outflows, in turn, regulate the environment, affecting how much fuel returns. Spin isn't just a feature, it's a governor on galactic ecosystems. But spin also evolves. A black hole doesn't necessarily form with high spin. It gains spin through the angular momentum of the matter it accretes. If the infalling matter arrives from a consistent direction, the spin builds steadily, like a wheel being pushed in the same direction over time. This is likely what happened to MCG 6-30-15. Over millions of years, it fed on a steady stream of gas, aligned in direction, boosting its spin close to the theoretical maximum. Alternatively, if the black hole experienced chaotic accretion, randomly oriented gas flows, mergers with other black holes, it might have ended up with a slower spin or even a fluctuating one. The fact that MCG 6-30-15 has such a high spin suggests a history of coherent, aligned accretion, perhaps fed by a large-scale structure of gas in the galactic nucleus that spiraled in with consistent angular momentum. Spin also plays a role in black hole mergers. When two black holes collide, the spins of each affect the final black hole's mass, spin, and even recoil velocity. In some configurations, the merged black hole can receive a kick strong enough to eject it from its host galaxy. So spin isn't just important for solitary black holes, it's a crucial factor in gravitational wave astrophysics, too. Ultimately, spin shapes the life cycle of a black hole. It controls how fast it grows, how it interacts with its surroundings, how bright it becomes, whether it produces jets, and how it ends up after mergers. It affects light, time, energy, and matter. Without understanding spin, we cannot understand how black holes sculpt the universe. MCG 6-30-15, then, is more than just a black hole with a fast rotation. It's a case study in cosmic dynamics, showing how spin can push physical processes to their limits. By studying this black hole, we learn not only about extreme environments but also about the role black holes play as architects of structure on the grandest scales. It is a reminder that deep in the heart of galaxies, there are invisible engines, spinning in silence, yet shaping everything. There's a natural fascination in extremes, especially when they touch the edge of what physics allows. When it comes to black holes, that extreme is spin. The black hole at the center of MCG 6-30-15 is spinning at more than 98% of the speed of light. That's not just fast. It's almost as fast as theoretically possible. But what does that mean? Is there a point where a black hole can spin too fast? A boundary beyond which nature says no further? The answer leads us into some of the most speculative, mysterious, and high-stakes territory in all of physics. First, we have to understand what's known as the spin parameter, or more formally, the dimensionless spin value. A star dot. This parameter ranges from 0, no spin, to 1, maximal spin. A black hole with a spin of A*= 1 is called an extremal Kerr black hole, a theoretical construct that rotates at exactly the maximum speed allowed by general relativity. For such an object, the ISCO hugs right up against the event horizon, and spacetime is twisted so violently that some physicists consider it a kind of edge case in Einstein's equations. MCG 6-30-15 central black hole has a spin estimated between A*= = 0.98 and 0.99. That is, within just a sliver of the theoretical maximum. It's right on the verge of extremality. But what happens if a black hole crosses that line? Could A** become greater than 1? In theory, if a black hole were to exceed this limit, it would no longer be a black hole in the traditional sense. The mathematical solution for a rotating black hole, the Kerr metric, predicts that if A** 1, the event horizon disappears, leaving behind a naked singularity. That's a region of infinite curvature exposed to the universe, without the veil of an event horizon to hide it. In such a case, causality, the order of cause and effect, could break down. Time travel, closed time-like curves, and other exotic phenomena might become possible. But this creates a problem. Physicists overwhelmingly believe that the universe forbids naked singularities. This belief is formalized in a hypothesis known as the cosmic censorship conjecture, which posits that singularities formed in realistic physical processes must always be hidden behind horizons. In other words, nature censors the most chaotic, unpredictable aspects of gravitational collapse. So if a black hole like the one in MCG 6-30-15 ever tried to spin faster than A*=1, some compensating process must kick in to stop it. And this leads to a deep question: how close can a black hole really get to extremality? There are some theoretical models suggesting that even approaching A*=1 becomes asymptotically difficult. That is, the closer a black hole gets to maximal spin, the harder it becomes to increase its angular momentum further. As matter falls in, the dynamics of energy and momentum conservation may self-limit the process. If the infalling matter brings too much angular momentum, it can be flung away before reaching the event horizon. Radiation pressure, magnetohydrodynamic instabilities, or relativistic feedback could all act as brakes, preventing the black hole from ever reaching the critical threshold. There's also the role of quantum effects. Some researchers believe that near the extremal spin limit, quantum corrections to classical general relativity become significant. These quantum effects might blur the event horizon, or cause the black hole to radiate spin energy in a way similar to Hawking radiation. Others propose that spinning too fast could lead to the generation of exotic states of matter or spacetime, possibly involving hypothetical particles like axions, or even triggering gravitational vacuum instabilities. This is the realm where string theory, loop quantum gravity, and other quantum gravity models start to offer competing visions. In string theory, for instance, a near-extremal black hole might be described by an ensemble of vibrating strings or d-branes, with the spin encoded in their configurations. In these models, there may be microstate geometries that avoid singularities altogether. But we lack observational tools to distinguish between these scenarios. Still, the implications are profound. If a black hole could somehow be pushed past the spin limit, say, by merging with another rapidly spinning black hole, could we produce a naked singularity? Could we detect its signature via gravitational waves, which would carry a unique imprint of such an event? The waveforms from mergers involving near-extremal spins are distinct and still not fully understood. Future gravitational wave observatories like LISA may help explore this frontier. It's also worth asking, is the black hole in MCG 6-30-15 already at the edge of physical possibility? If its spin were even slightly higher, would the iron line profile change in ways our models cannot reproduce? Are we seeing the natural spin ceiling enforced by physics, or just a coincidence of how this black hole formed? To investigate that, astronomers look at spin measurements across many systems. So far, the distribution of observed spins in supermassive black holes suggests that high spin values are not uncommon, but true extremality, A*=1, has never been confirmed. The black hole in MCG 6-30-15 remains one of the fastest measured, but even it falls just short of the theoretical boundary. Could this be more than coincidence? Perhaps the universe is fine-tuned to never allow extremal spins. Or perhaps the models we use to estimate spin, based on accretion disk geometry and X-ray spectra, are missing subtle effects that cap our confidence levels. The possibility that no black hole reaches spin=1 might be telling us something deep about the limits of spacetime itself. There's another interesting twist. A black hole's spin might even decrease over time. Energy extraction mechanisms, like the Penrose process or Blandford's Najek jets, tap into rotational energy. Over cosmic timescales, a black hole that emits powerful jets or interacts with magnetic fields could gradually lose angular momentum, spinning down like a cosmic gyroscope encountering resistance. So even if a black hole could reach A*=1 momentarily, it might not stay there for long. The universe seems designed to approach limits, but never quite reach them. MCG 6-30-15 shows us just how close one can get, flirting with a boundary beyond which space and time themselves may behave in unpredictable ways. In the end, the spin of a black hole is not just a number. It's a statement about what physics permits, about where theory ends and speculation begins. And as we study objects like MCG 6-30-15, we are not merely measuring astronomical parameters. We are mapping the contours of the possible, and brushing against the edge of reality as we know it. A black hole doesn't just begin its life spinning wildly at nearly the speed of light. Its rotation, its incredible, almost unthinkable spin, is something earned over time, shaped by the cosmic dance of matter and energy falling into its grasp. In the case of the black hole at the center of MCG 6-30-15, which spins at more than 98% the speed of light, the journey to such a state is a story written over millions, even billions of years. A story not just of devouring mass, but of direction, consistency, and the strange and selective way that gravity rewards order. To understand how a black hole ends up spinning so fast, we have to first recognize what spin is, physically. Spin isn't motion in the everyday sense. The black hole itself has no surface, no solid edge that's rotating. Instead, its spin is a fundamental property of the spacetime it occupies, a twist in the very geometry of the universe surrounding it. And this twist, or angular momentum, builds up when the black hole absorbs matter that's also rotating. Imagine a swirling whirlpool at the center of a galaxy, with gas and dust spiraling into it. If this material is rotating in a consistent direction, always clockwise or always counterclockwise, then every bit of mass that falls and adds angular momentum in the same orientation. The black hole accumulates this spin slowly, incrementally, over vast time. It becomes like a cosmic flywheel. The more aligned mass it consumes, the faster it spins. This is the key to how the black hole in MCG 6-30-15 likely reached such incredible speeds. It didn't simply gobble up matter, it gobbled smart, feeding in a highly directional and coherent way. The accretion disk around it wasn't random or chaotic. It was organized. It fed the black hole steadily, like a record spinning under a needle. And this directionality is vital. Because if the black hole had been fed with matter falling in from all directions, some rotating one way, some the other, those angular momenta would cancel out. The black hole might gain mass, but its spin would remain slow or erratic. Instead, what happened here was a sustained, directional accretion flow, probably lasting millions of years. This kind of feeding requires stability in the galactic nucleus. The gas that flows inward has to maintain its angular momentum over long periods. In a galaxy like MCG 6-30-15, this could happen if there were a steady gas inflow from a galactic bar or spiral arms, funneling material inward along defined lanes. Or, the galaxy might have undergone minor mergers with smaller galaxies, bringing in fresh material that added to the disk without disrupting its orientation. These events don't have to be violent. They can be surprisingly smooth, especially if the incoming galaxies approach from favorable angles. Once a black hole starts spinning, an interesting feedback loop begins. A spinning black hole drags spacetime around it, frame dragging, twisting the orbits of infalling gas. If new material tries to fall and misalign with the black hole's spin, it gets torqued into alignment by this effect. So the spin itself tends to stabilize the orientation of the accretion disk over time. In essence, a spinning black hole encourages more material to feed it in the same direction. This process, known as the Bardeen-Pedersen effect, causes the inner disk to warp and realign with the black hole's equatorial plane, reinforcing spin alignment further. This is one reason why black holes can reach such high spin values despite occasional disruptions in their feeding. Once enough spin has built up, the black hole becomes resistant to change. Only major events, like a merger with another black hole spinning in the opposite direction, can significantly alter it. Now there's a flip side to this, chaotic accretion. If a black hole is fed in short, random bursts from different directions, its spin remains low. Each feeding event adds angular momentum in a different direction, effectively scrambling the black hole's orientation over time. This tends to produce low or moderate spin black holes. But in MCG 6-30-15, the extreme spin tells us that such chaotic feeding didn't dominate its past. Instead, it had a long, quiet, efficient meal, perhaps a gas-rich phase early in the galaxy's history, or a prolonged inflow from a stable structure like a circumnuclear disk. There's also the possibility that the black hole's spin started high. black holes formed from the collapse of massive stars can inherit the angular momentum of their progenitors. If the star was spinning rapidly, the black hole might be born with a significant spin. However, simulations suggest this initial spin is rarely extreme, more likely in the range of *= 0.5 to 0.7. To push a black hole all the way to *= 0.98 or beyond, accretion is required. Interestingly, this gives us a glimpse into the black hole's past. The spin value we see today is a fossil record of its growth history. It tells us not just how much the black hole has eaten, but how it ate. A black hole that's grown through random, violent mergers will be massive but sluggish. One that grew via quiet, directional feeding will spin like a top, and shine brightly because of it. It's also worth noting that as a black hole's spin increases, so does its radiative efficiency. This means it gets brighter, hotter, and more influential, producing more energy per unit of infalling mass. So spin becomes a kind of feedback amplifier. The more it spins, the brighter it becomes. The brighter it becomes, the more it heats and stirs its environment, potentially regulating further feeding. This could help explain why we don't see many black holes spinning at exactly *= 1. The environment eventually responds to the black hole's brightness and shuts off the supply. So how did MCG 6-3015's black hole get so fast? By feeding with precision. By drawing in matter from a consistent direction. By maintaining that feeding over long stretches of galactic time. And perhaps, by starting with a small push from its birth and building from there, gradually accelerating its twist on spacetime until it neared the ultimate speed limit that nature allows. In the end, the black hole's spin is a story of alignment, of galaxies, of gas clouds, of the gravitational rhythm of the cosmos. It is not chaos, but coherence, that leads to such extremity. MCG 6-30-15 shows us how the universe, when left undisturbed, can wind itself tighter and tighter, until it becomes a singularity wrapped in rotation, a place where even light must obey the spin. As gas spirals inward toward the event horizon of a black hole, it doesn't just heat up and glow, it becomes tangled in one of nature's most invisible yet powerful forces, magnetism. Magnetic fields, though unseen, play a critical role in shaping the physics of accretion disks and, more profoundly, in controlling the spin behavior and energy output of black holes like the one in MCG 6-30-15. At first glance, one might assume that the swirling gas around a black hole is governed purely by gravity and orbital mechanics. But embedded within this plasma are magnetic field lines, twisted and contorted by motion, stretched taut by differentially rotating layers of gas, and sheared by turbulent instabilities. As the gas moves, these magnetic fields act like invisible scaffolding and levers, exerting torques that can extract angular momentum and energy from both the accretion disk and the black hole itself. One of the most important magnetic phenomena in this environment is the magnetorotational instability, MRI. This instability allows the angular momentum of the inner disk material to be transported outward, enabling material to move inward toward the black hole. In simple terms, MRI is the reason accretion disks can actually feed black holes. Without it, the disk would just sit there, spinning, unable to shed angular momentum. The process depends heavily on magnetic fields to function. It's magnetic tension that enables momentum exchange between gas layers. But the story goes even deeper. Magnetic fields near the black hole's event horizon can thread through the black hole itself, connecting it to the outer regions of the disk or to a surrounding corona of hot, ionized gas. This threading opens the door to energy extraction mechanisms like the Blandford's-Nagic process, which pulls rotational energy directly from the black hole via these field lines, launching powerful outflows and possibly jets. Now, in MCG 6-30-15, we don't see large-scale relativistic jets, but that doesn't mean magnetic activity is absent. In fact, the iron K-alpha line's strength and structure suggest a magnetically active corona, a zone of high-energy particles suspended above the disk by magnetic loops. These coronal flares bombard the disk with X-rays, lighting up the inner regions and producing the spectral fingerprints that let us study the black hole's spin. Crucially, magnetic fields may also regulate how close to the speed of light the black hole can spin. They provide a kind of magnetic braking mechanism. By exerting stress on the disk and black hole, they can slow the rotation slightly, preventing the spin from ever reaching the true theoretical limit. It's yet another sign that even in the most extreme environments, order emerges from invisible forces, sculpting the very nature of the cosmic engine. When we speak of a black hole spinning at nearly the speed of light, we're not just describing a faster version of a regular black hole. We're invoking an entirely different solution to Einstein's field equations. This is the Kerr solution, a mathematical model that describes how spacetime behaves around a rotating mass. And in the case of MCG 6-3015's black hole, spinning at over 98% of light speed, we are witnessing a textbook example of a Kerr black hole, a region of space where the rules of general relativity are pushed to their most elegant and extreme. Discovered by New Zealand mathematician Roy Kerr in 1963, the Kerr solution was the first exact solution to Einstein's equations that described a rotating black hole. Before this, the only black hole solution we had was the Schwarzschild solution, which describes a static, non-rotating black hole. While useful, the Schwarzschild black hole is a simplification. Almost no real black holes are born without spin. Stars rotate, galaxies rotate, and so do the black holes they produce. The Kerr black hole, then, is the real deal. It has two key parameters, mass and angular momentum, or spin. Unlike the Schwarzschild black hole, which has a perfectly spherical event horizon, a Kerr black hole has an oblate, flattened event horizon due to its rotation. But more importantly, its rotation twists the very fabric of spacetime around it. This effect, frame dragging, is unique to rotating objects in general relativity, and it is most pronounced in extreme Kerr black holes like the one in MCG 6-30-15. The region outside the event horizon where this twisting occurs is known as the Ergosphere. In the Ergosphere, spacetime is dragged along so violently that no object can remain stationary with respect to the distant universe. Any particle that enters this region is forced to rotate around the black hole, even if it doesn't fall in. It is here that processes like energy extraction via the Penrose mechanism or the Blandford's-Najek process become possible. These phenomena are only permitted in the geometry of a Kerr black hole. And it gets stranger. The Kerr solution predicts that inside the black hole, beyond the event horizon, the singularity is no longer a point. Instead, it forms a ring. This ring singularity opens the door to a hypothetical interior structure that could contain a wormhole, or even a time loop, though these remain purely theoretical and are likely unstable in the real universe. For MCG 6-30-15, its extreme spin means it fits almost perfectly into the Kerr model. The observations of broadened iron lines, light echoes, and warped accretion disks are all phenomena predicted by the Kerr metric. Everything we detect in X-rays, every distortion of space and time, maps back to this rotating solution of Einstein's equations. In studying MCG 6-30-15, we're not just observing a black hole, we're watching the Kerr geometry in action, confirming the most precise and complex predictions of general relativity. For all we've uncovered about MCG 6-30-15 and its astonishing spin, so much remains wrapped in shadow, both figuratively and literally. Black holes are notorious for keeping their secrets, and even with tools as advanced as XMM Newton and Chandra, the cosmos only offers whispers where we want revelations. This particular black hole has helped illuminate the nature of relativistic gravity and accretion, but it has also deepened some of the most pressing mysteries in astrophysics. What we still don't know could one day change everything we think we understand about black holes and the universe itself. One of the most persistent mysteries is why MCG 6-30-15 doesn't appear to produce relativistic jets, despite its incredibly fast spin. In many systems, rapidly rotating black holes are seen launching massive jets of plasma that shoot thousands of light-years into intergalactic space. These are powered, in part, by the Blandford-Najek process, a mechanism that extracts rotational energy via magnetic fields anchored in the accretion disk and black hole. But in this case, the jets are absent or undetectable. Could it be a limitation of our instruments? Are there jets being launched, but they are aligned in such a way that we simply can't see them? Or are the magnetic field configurations in the system insufficient to support jet formation? Perhaps there's something about the geometry of the disk or the surrounding environment that quenches jet activity. Understanding this discrepancy isn't just an academic question, it cuts to the core of how energy is distributed in the universe. Jets can regulate star formation, heat galactic halos, and shape entire galaxies. Knowing why they appear in some systems, but not others, is essential to building a complete picture of galactic evolution. Another unresolved question lies at the very origin of the black hole's spin. While we've explored the idea that directional accretion over time can build up such high angular momentum, we still don't know with certainty what path MCG 6-30-15 took. Was it born spinning rapidly from a progenitor star with exceptional angular momentum? Did it acquire most of its spin through consistent accretion in a quiet, stable environment? Or was it the result of a black hole merger, in which two already spinning black holes combined and transferred their rotational energy into the final object? Each of these pathways implies different histories, not just for the black hole, but for the galaxy itself. If the spin was achieved by steady feeding, then the galaxy's center has likely been dynamically calm for a very long time. If it was due to a merger, then a violent episode in the past left behind this rotational relic. Yet the observational evidence doesn't clearly favor one over the other. Until we can peer deeper into galactic centers or simulate black hole evolution with higher resolution and precision, the spin origin will remain largely speculative. A deeper, more philosophical question lingers as well. Is this behavior common or rare? Is MCG 6-30-15 a cosmic outlier, a strange, finely tuned system that happens to have the perfect conditions for extreme spin and strong relativistic effects? Or is it the tip of the iceberg, one of many fast-spinning black holes that we simply haven't yet resolved? There's a danger in generalizing from one extraordinary case. While a handful of other black holes have been measured with high spins, few reach the extremity of MCG 6-30-15. If these systems are rare, they might hint at uncommon evolutionary histories. But if they are common, that changes the paradigm. It suggests that the universe regularly builds these monsters, and that fast-spinning black holes might be central to how galaxies evolve, interact, and even light up across cosmic time. This opens up a whole new area of exploration. How does spin distribution vary across black holes of different sizes and environments? Is spin correlated with black hole mass, or with the type of galaxy that hosts it? Are high-spin black holes more likely to be found in younger galaxies, or in ancient, gas-rich ones? We don't yet know. The current dataset is simply too limited to draw statistically robust conclusions. And then there's the ultimate question: are we missing something fundamental? Could our models, even now, be incomplete? Are we misinterpreting data through the lens of existing theory, when an entirely new framework might explain things more clearly? For instance, could some of the broadened iron lines and warped disk phenomena we see be better explained by quantum gravitational effects, or exotic alternatives to general relativity? Could dark matter interactions or unknown particles influence black hole spin dynamics in ways we've never considered? Each new observation adds a layer to the mystery, not just resolving old questions but prompting entirely new ones. The story of MCG 6-30-15 is far from complete, and that's what makes it so compelling. It is not just a scientific object of study, it is a cosmic invitation to keep looking deeper, to keep refining our models, and to keep challenging what we believe is possible. What we've learned about MCG 6-30-15 so far, its incredible spin, its warped spacetime, its broadened iron emission lines, all of that has been made possible thanks to the powerful eyes we've already placed in orbit. Observatories like XMM Newton and Chandra have given us detailed glimpses into the high-energy cosmos, revealing clues hidden in X-ray light that never reaches Earth's surface. But these tools, as powerful as they are only the beginning. As we peer further into the 21st century, new missions are being designed and prepared, Athena and Lynx, each promising to push our understanding of black holes like MCG 6-30-15 into entirely new territory. The Advanced Telescope for High-Energy Astrophysics, or Athena, is a European Space Agency mission planned for the late 2030s. Its mission: to observe the hot and energetic universe with far greater sensitivity and precision than anything we've had before. Athena will be equipped with two revolutionary instruments: the Wide Field Imager, WFI, and the X-ray Integral Field Unit, XIFU. These tools won't just capture X-ray light. They'll break it down with extreme precision, allowing astronomers to map the motions of matter and energy near black holes with unprecedented detail. For MCG 6-30-15 and similar systems, Athena could revolutionize our understanding of how relativistic effects shape emission spectra. Its XIFU will allow us to measure the velocity and temperature of different regions of the accretion disk in real time, resolving features in the iron K-alpha line that current telescopes can only blur together. We'll be able to distinguish the inner disk dynamics, see how matter accelerates as it spirals inward, and catch subtle shifts in the line's shape that reveal short timescale fluctuations in the corona and disk geometry. This could finally confirm whether the warps we suspect in the inner disk are stable structures or constantly shifting ripples, stirred by magnetic turbulence, or frame dragging. Then there's LINX, a proposed next-generation X-ray observatory from NASA. Though still in the conceptual phase, LINX is designed to have 100 times the sensitivity of Chandra, with far finer spatial resolution and broader spectral capabilities. If launched, LINX would be able to resolve the X-ray structure of even faint black holes across vast distances, potentially identifying many more MCG 6-30-15 like systems that have so far gone unnoticed. It could detect reverberation echoes from flares near the event horizon, tracing them back to their origin point with such precision that we might one day map the curvature of spacetime itself near the black hole. Both of these missions will help answer the lingering questions about spin. How common is near-maximal spin in black holes? How does it evolve over time? Can we directly see the twisting of light paths, the effects of frame dragging, the precession of warp disks? Can we detect tiny deviations from general relativity's predictions, suggesting quantum corrections or new physics near the event horizon? And perhaps most excitingly, these telescopes may provide the data needed to test alternative models. Could there be dark matter interactions affecting the inner disk? Is the black hole surrounded by exotic matter or scalar fields that influence its spin or radiation profile? Only sharper data with the clarity and sensitivity of Athena or LINX, can begin to answer these frontier questions. In a universe where the strangest truths are hidden in the smallest fluctuations of light, these future missions are not just upgrades, they're gateways. They will take us closer to the event horizon, closer to the singularity, and closer to answering whether our most cherished theories hold true when gravity is at its strongest. For most of us, a black hole like the one in MCG 6-30-15 seems impossibly distant, 130 million light-years away in a galaxy we can't even see with our naked eyes. It exists beyond the reach of our senses, beyond the bounds of our daily lives. So why should it matter to us? Why should we care about something so remote, spinning so fast, devouring light in a corner of space we'll never visit? Because black holes are not just cosmic curiosities. They are architects of galaxies, engines of transformation, and time capsules of the universe's history. They shape the very cosmos we live in, not just through their gravity, but through the energy they unleash, the matter they scatter, and the space they distort. MCG 6-30-15's black hole, spinning at nearly the speed of light, may seem silent and contained, but it affects everything around it. Its powerful gravity influences the orbits of stars and its galaxy. Its radiation, emitted through the heat and chaos of infalling matter, bathes the central region of the galaxy in high-energy X-rays. That radiation can heat interstellar gas, quench star formation, or trigger new stars to be born, depending on how it's distributed. Over millions of years, this interaction between black hole and galaxy is what shapes the evolution of the entire galactic ecosystem. In fact, the relationship between black holes and galaxies is one of the most profound in modern astrophysics. The mass of a galaxy's central black hole correlates tightly with the mass of its bulge, a connection known as the m-sigma relation. It suggests that the growth of black holes and galaxies is intimately linked, as if galaxies can't fully form without the presence of a black hole, and black holes can't fully grow without their host galaxies feeding them. So by studying extreme black holes like MCG 6-30-15, we're also studying how galaxies like our own Milky Way came to be. We're uncovering how the universe organizes itself at the largest scales. And more than that, we're testing the laws of physics themselves in the most extreme environments imaginable. General relativity, quantum mechanics, thermodynamics, all of them are pushed to their limits in places like this. Every time we measure a gravitational redshift, or see frame dragging distort light, or watch a broadened iron line flicker with the spin of a warped disk, we're asking, does the universe still follow the rules? And if it doesn't, what comes next? There's also a deeper reason. A more human one. When we look at MCG 6-30-15, we're looking into a mirror, one that reflects the wild, strange, untamed edge of reality. It reminds us that the universe is not just a calm expanse of stars, but a place where light itself bends, where time stretches and breaks, where matter can vanish behind a horizon and never return. These are not just facts of physics. They are poetic truths about the nature of existence. The black hole at the heart of MCG 6-30-15 may never touch us, but it speaks to the forces that built the universe we live in. To understand it is to understand ourselves, not just as humans on Earth, but as citizens of a universe governed by gravity, time, and a relentless march toward entropy. To study it is to say, we are here, and we are listening. Because even from 130 million light-years away, this black hole is telling a story. And it's one we can't afford not to hear. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.